Now let's take a look at how this course is structured and what you can expect to learn in each chapter. I have carefully designed this course into 9 chapters, structured around practical use cases and real-world project scenarios you are likely to encounter. Chapter 1, OAuth 2 Basics. This foundational chapter is the cornerstone of the entire course, and arguably the most critical one. Here you will master the core concepts of OAuth 2, laying the groundwork for everything we will explore later. We will cover what OAuth 2 is, why it is needed, its key components, how it works, and the essential elements you will use in the subsequent chapters. If you are new to OAuth, this is your must-watch chapter before moving forward. Chapter 2, User-Initiated Flows. In this chapter, we will dive into OAuth 2 flows involving users, designed for web browsers, mobile applications, and desktop applications. For each flow, we will explore its step-by-step workings, the challenges it addresses, and its ideal use cases. By the end, we will summarize all the flows and guide you through a decision tree to help you choose the right one for your specific project requirements. Chapter 3, OAuth 2 Security Extensions for User-Initiated Flows. Security is an ever-evolving pursuit. While many OAuth 2 flows are inherently secure, certain high security requirements call for additional layers. In this chapter, we will examine several OAuth 2 extensions that address specific challenges and elevate security to their next level. We will explore each mechanism step by step, focusing on the configurations and the checks required to implement them effectively. As always, we will conclude with the practical use cases and a decision tree to help you apply these techniques in real-world projects. Chapter 4, Resource Owner Password Credentials Flow. This chapter covers a unique but risky flow. While it is generally not recommended, there are rare cases where it might be your only option. We will explore the scenarios where this flow could be necessary, the associated risks, and the strategies to mitigate those risks if you choose to implement it. Chapter 5, Machine-to-Machine Flows. The Client Credentials Flow. OAuth 2 is not just for user-initiated interactions, it's also for machine-to-machine communication. If you are working on backend services, enterprise applications, or automated jobs, this chapter will show you how to implement the Client Credentials Flow and when to use it. At the end of this chapter, we will explore practical use cases and provide a decision tree to guide you in determining when to use this flow or consider alternatives. Chapter 6, Device Code Flow. Even devices with limited input capabilities, like smart TVs and printers, can utilize OAuth 2. This chapter walks you through the device code flow with a step-by-step example inspired by a Netflix login on a smart TV. You will learn how to implement this flow effectively and securely in such constrained environments. Next, integrating external identity providers with JWT and SAML assertions. In many projects, user authentication needs to occur via an external identity provider. This is common in compliance-driven environments, trusted partner integrations, or phrased migrations. In this chapter, we will explore bridging flows that enable seamless integration with external systems like SAML or JWT-based providers. You will gain insights into when these approaches are essential and how to implement them successfully. Chapter 8, Advanced Client Authentication Methods. In secure applications, servers must authenticate themselves, not just the users. This chapter delves into advanced client authentication methods available in OAuth 2, starting from basics methods and advancing to sophisticated mechanisms. You will learn how to meet varying security levels. We'll explore each method step by step and provide a comprehensive comparison table to help you decide when and how to use each option based on your project's security requirements. Chapter 9, Advanced Access Token Security. Access tokens are the keys to your resources, but they can be stolen or compromised. In this final chapter, we will address the critical challenge of securing access tokens. You will learn about various mechanisms to enhance token security, explored step by step, and understand the use cases for each. By the end of this chapter, you will know how to implement these advanced techniques to protect your systems. Between chapters, I've included practical exercises to make sure you have understood the concepts clearly before moving on to the next chapter. Before diving into the course, I want to share a few tips to help you get the most out of it and make your learning experience as effective and enjoyable as possible. Adjust the playback speed. Udemy offers a handy feature to speed up or slow down the video playback. If you feel I am speaking too fast or too slow, make use of this function to follow along at a pace that's comfortable and clear for you. Tailor the course to your needs. This course is designed to accommodate both beginners and advanced learners. If you are new to OAuth 2 and want to master it, I recommend going through the entire course from start to finish. For a solid foundation, focus on Chapter 1, 2, 4, and 5, which cover the basics comprehensively. For advanced learners, if you are already familiar with OAuth 2 but want to explore advanced topics, focus on the chapters that cover mechanisms you are less familiar with. Chapter 3, 7, 8, and 9 are ideal for diving into advanced concepts. However, if you find yourself needing a refresher on the basics, don't hesitate to revisit them first. Customize based on your project requirements. If you are here to address specific project needs, start with the basics and then focus on the chapters relevant to your use case. For instance, Chapter 2 is perfect for user-initiated flows, while Chapter 9 is invaluable for securing access tokens with advanced mechanisms. Lesson prerequisites. In each lesson, I have tried to highlight any prerequisite chapters or concepts you should review before proceeding. This ensures you have a strong foundational and can follow along easily. With these tips in mind, you are all set to make the most of this course and tailor it to your unique needs. Now let's get started. In this chapter, we are going to explore the basics for OAuth 2. We'll start by discussing why OAuth 2 was created and why it is crucial for secure data sharing. We will uncover this need through an engaging story about Sam Snapster, a friendly guy who loves taking selfies and sharing them on Instagram with his followers. Next, we will look at how applications like Facebook and Google use OAuth 2 to let other applications access user data securely. We will walk through a real-world scenario that will guide us into understanding the standard OAuth 2 flow and its roles. Then, we will identify the key players in OAuth 2 and see how they collaborate to secure data. We'll map the components from our scenario to the technical OAuth 2 flow and roles and understanding their responsibilities. After that, we will dive into a live demo using Photobee application to see everything we have learned in action. In this demo, I will be the resource owner granting access to my OneDrive photos using OAuth 2. We'll discuss the different types of clients that use OAuth 2, including single-page applications, mobile applications, desktop applications, and server-side applications. We'll explore the differences between them and determine when to use each client type. We'll learn how OAuth Scopes define what data an application can access and how they limit permissions to enhance security. First, we will start with an introduction. We will cover what scopes are and why they are important for controlling access to API resources. Next, we'll discuss how to structure and name scopes effectively, ensuring they are both granular and manageable. Finally, we will look at different methods for deriving the needed scopes, whether from business processes, API structure, or role-based access control, while also considering audit and compliance needs. We'll delve into the various types and formats of tokens that OAuth 2 uses. We'll explore access tokens and refresh tokens, their differences, and how they can be used together. Additionally, we will discuss token formats such as structured JWT tokens and unstructured opaque tokens, their differences, and the scenarios in which each format is suitable. We'll discuss how to ensure the validity and security of tokens in an OAuth 2 setup. We'll explore two mechanisms: token introspection, online validation, and self-contained token validation, offline validation. We'll delve into how introspection works to validate tokens in real time. Similarly, we'll examine how self-validation functions using symmetric and asymmetric signing algorithms, providing better architectural implementation. We'll begin with a simple scenario involving Bob, Alice, and an evil guy, man-in-the-middle attacker who wants to cause trouble in the relationship. As usual, we'll then map the scenario's components to the technical aspects and flows, helping us understanding the validation mechanisms. By the end, you will have a clear understanding of how and why to configure your services for OAuth 2 token validation. We'll wrap up with a comprehensive comparison that will help us make informed decisions on which mechanism to use in different situations. Finally, we will introduce OpenID Connect and see how it builds on OAuth 2 to provide seamless user authentication and identity management. We will begin with a brief introduction, move on to a comprehensive comparison, and conclude with a practical scenario. You will become familiar with terms like ID token, user info endpoint, and more. By the end of this chapter, you will have a solid understanding of OAuth 2 basics and how it helps secure data and APIs across various applications. Let's get started. Before we dive into how OAuth 2 works and all the technical details, let's start with a story to understand why OAuth 2 is needed. Meet Sam Snapster. Sam is a fun-loving, energetic guy who absolutely loves taking selfies. He is always capturing every moment with his phone and sharing these snapshots with his friends and followers on Instagram. Whether it is a beautiful sunset, a delicious meal, or a spontaneous dance, Sam makes sure his followers do not miss a single moment. Sam has hundreds of thousands of photos, so he stores them all in OneDrive where he has terabytes of space. To make his photos even more amazing, Sam uses photo editing application called Magic Snap. Because it offers great effects and can even enhance his photos if he just woke up or didn't look his best, just like this here for example. But here's the problem. Because his photos are on OneDrive, Sam does not want to go through the hassle of downloading them to his phone and then uploading them to his application. He wants an easier and a better way so that Magic Snap can access his photos directly from OneDrive for editing. However, when the application tries to do this, OneDrive rejects the request saying it's unauthorized. So Magic Snap then asks Sam for his username and password to sign in and get the photos. The application says, "Hey Sam, I tried to fetch your latest photos from your OneDrive, but it was rejected because I need access. Please give me your OneDrive username and password here and I will fetch the photos for you immediately." Now Sam is not comfortable sharing his credentials with the Magic Snap. What if he uses other applications? Does he have to give every application his credentials? These applications could misuse his information or access more than just his photos. Sam worries about his personal documents and private data being exposed. And this is where OAuth 2 comes to the rescue. OAuth 2 is a secure and convenient way to give third-party applications access to your resources on your behalf without sharing your passwords. With OAuth 2, Magic Snap can access Sam's photos in his OneDrive account without needing his password and credentials. Sam can select the specific photos he wants to share, and those are exactly what Magic Snap can access and see. Now that we understand why OAuth 2 is needed, let's see what benefits it brings to the table for Sam. No more sharing passwords. Sam no longer needs to share his password with multiple applications. This reduces the risk of his credentials being misused or compromised. Easy access control. Sam can easily grant and revoke access to his OneDrive account for different applications. This gives him complete control over who can access his data and when. Specify access. Sam can specify exactly what each application can access. This means he can allow Magic Snaps to access only some of his photos that he selects without giving it permission to see his documents, calendar, or other private data. Sam is now excited. He can now edit his photos without any security worries and share them with his followers on Instagram. And guess what? Sam is not alone. Major services like Google, Facebook, and Amazon all use OAuth 2 to keep their users safe. So the next time you log into a new application with your Google account, you are using OAuth 2. OAuth 2 stands for Open Authorization 2. Now, let's dive deeper and explore how a traditional OAuth 2 flow works. To understand how the standard OAuth 2 flow works, let's start with a real-world scenario about Alex's vacation. We will then map the characters and the flow to the technical roles and the processes in OAuth 2. Meet Alex, a vacation-loving adventurer who enjoys traveling to various destinations and discovering the world. Alex is thrilled because he's about to embark on a 6-month vacation to Thailand. But there is a challenge. Alex owns several properties and a car, and he needs someone trustworthy to manage them while he's away. So Alex turns to his reliable brother Sam and asks him to handle renting and selling his assets during his trip. Sam eagerly steps in and tries to rent out the car and sell the greenhouse. But there is a hitch. The authorities stop Sam because he is not the owner and lacks authorization to manage these properties. They require an authorized declaration from Sam. Sam contacts Alex and says, "I am glad I reached you before you left. I cannot proceed without an authorized declaration from you." Alex hits straight to the notary and says, "Hi, here is my ID. I need to make a notarized declaration for my brother to rent my car and sell my greenhouse." The notary verifies Alex's ID and ownership of the properties, then asks, "Can you please review and confirm this information?" Sam is allowed to rent you car on your behalf. Sam is allowed to sell you greenhouse on your behalf. Alex checks everything and confirms. "Yes, everything is correct. You have my approval." Then the notary says, "Great, here is the notarized declaration. Have a fantastic trip. Bye-bye." Alex hands the notarized declaration to Sam, saying, "Now you are officially authorized to manage these properties. Thanks, I've got to catch my flight to Thailand. Bye-bye." With everything sorted, Alex jets off to Thailand, excited to take selfies on the beach and with elephants. Armed with the notarized declaration, Sam returns to the authorities and says, "I have the official authorization. I would like to rent the car and sell the greenhouse." The authorities respond, "All set, you are good to go," and it works perfectly. So now, let's see how this real-world scenario relates to the OAuth 2 standard flow. Let's start by mapping the characters to OAuth 2 roles. Alex is the resource owner, because he owns the resources. Sam is the client, because he is trustworthy and should be granted access to the resource owner's resources. The notary is the authorization server, because he verifies the identity of the parties and issues trusted documents, notarized declarations that are recognized by the authorities managing the resources of the resource owner. The authorities represent the resource server, which controls access to resources like cars and houses, and can verify the notarized declarations. And the notarized declarations issued by the notary in the OAuth 2 context are called access tokens. In the example of the previous lesson with Sam Snapster, Sam was the resource owner, the Magic Snap application was the client, OneDrive was the resource server, and the authorization server was likely Microsoft's Azure Active Directory, where you would typically enter your username and password to log in. Now let's map the flow to the technical standard OAuth 2 flow. Here is how it works. The resource owner initiates the flow and asks the trusted client to fetch his resources from the resource server on his behalf, just like Alex when he asked his brother to rent and sell his assets. The client then redirects the resource owner through a user agent, like a browser, to the authorization server to authenticate and obtain an access token. Just like Alex, going to the notary presents his ID and get a notarized declaration for Sam. And in this way, you don't have to give your username and password to third-party applications. You only share them with your trusted authorization server. The resource owner provides his credentials, such as a username and password, and the authorization server verifies them. The authorization server then asks the resource owner to review the permissions that will be granted to the client. If the resource owner agrees, the authorization server issues an access token. The client receives the access token and uses it to authorize its request to the resource server to fetch the resource owner's resources on his behalf, just like Sam presenting the notarized declaration to the authorities to authorize himself to rent and sell Alex's assets. Finally, the resource server verifies the access token, and if everything checks out, it grants the client access to the requested resources or the ability to perform the desired actions on behalf of the resource owner. I know you might have many questions swirling around in your head right now. We have multiple OAuth 2 flows, each working a bit differently, but don't worry, we will dive into all of them in the upcoming sections. We will explore the various OAuth 2 flows, extensions, client types. We will also take a closer look at how permissions are reviewed and granted. We will discover all of this together in detail. So up until this point, we have mapped the characters from our story to the technical OAuth 2 roles, and we have also aligned the real-world scenario with the standard OAuth 2 flow. Now let's quickly recap these roles to solidify our understanding. Resource owner. This is the entity that owns the data and resources being accessed. The resource owner has the power to grant or deny permissions for data access. Client. The client is the application or entity that requests access to the resources on behalf of the resource owner. Clients can be a third-party application, like a single-page application running in a browser, known as a public client. a backend server or enterprise application known as the confidential client. We will dive deeper into the different types of clients in a later lesson, where we will discuss when and how to use each type effectively. In essence, Alex as the resource owner is like the property owner who controls access to his assets. Sam as the client is like the trusted brother who needs permission to manage those assets on Alex's behalf. Resource server. The resource server hosts the protected resources and data that the client wants to access. Its primary role is to validate the access tokens that the client presents before allowing access to the resources. If the token is valid, the resource server grants access to the requested data or performs the requested actions. Authorization server. The authorization server is responsible for authenticating the resource owner. It ensures that the resource owner's identity is verified before any access is granted. Once the resource owner is authenticated, the authorization server issues access tokens to the authorized clients. These tokens serve as a form of proof that the client has permission to access the resource owner's resources on their behalf. In essence, the authorization server is like the trusted notary who verifies identities and issues notarized documents, while the resource server is like the authority that checks these documents before allowing any actions to be carried out. Now that we have covered the OAuth 2 roles and standard flow, it's time to see it all in action. In our next lesson, I will demonstrate everything we have learned using a photo editing application and OneDrive. We will work through each step of the process, showing how OAuth 2 works behind the scenes to keep your data secure. So let's get ready to bring everything we have covered so far to life. In this lesson, I will demonstrate the standard OAuth 2 flow. But before we dive into the demo, let me briefly introduce the components we will be working with. I'm going to be the resource owner using a photo editing application called PhotoBee to enhance my photos stored in OneDrive. PhotoBee acts as the OAuth 2 client, the third-party application that I want to grant access to my photos in OneDrive. OneDrive in turn serves as the OAuth 2 resource server where my resources are securely stored. Lastly, the Microsoft Authorization Server is the entity that Microsoft uses to manage access to OneDrive. Okay, let's get started by opening the PhotoBee OAuth 2 client. So I am now in PhotoBee. Here you can see options for dragging photos to edit, whether from your device locally or from online sources like Dropbox, OneDrive, Google Drive, and so on. I'm going to select OneDrive. Give PhotoBee direct access to your OneDrive. I will click on that. So in this new window, we are redirected to the Microsoft Authorization Server for OneDrive. This is the server we typically log into when accessing our resources in OneDrive. This means I am sharing my credentials only with my trusted authorization server, Microsoft, and not with each application that needs access. Let me expand the window a bit here. Okay, in the URL you notice that Microsoft uses OAuth here. Here is the authorize endpoint, which we will explore in more detail later. You see here also the client ID, which is the OAuth 2 client ID for PhotoBee, formatted as a UUID. There are also OAuth 2 scopes. These represent the permissions we are granting to the PhotoBee client. In this case, it's full access, including read and write permissions. We will delve into scopes in detail in a future lesson. The response type is set to token, which is tied to the specific OAuth 2 flow being used, and we will cover this in upcoming lessons. Finally, the redirect URI is the URL where the Microsoft Authorization Server will redirect me as resource owner after successful authentication, providing an access token for PhotoBee. Now, as the resource owner, I need to authenticate with my authorization server by entering my email address and password. So after submitting my credentials, I will be asked here, like you see, to review the permissions I am granting to PhotoBee. Have full access to all files you have access to. This means PhotoBee will be able to read, create, update, and delete all OneDrive files that I can access. Accepting these permissions means that I am allowing this app to use my data as specified in its term of service and privacy statement. You can change these permissions at this address here. And if I click here on show details, only accept if you trust the publisher and if you selected this app from a store or website you trust. Microsoft is not involved in licensing this application to you. This is why the client must be trustworthy. Like I said before, Microsoft warns the resource owner here to be careful, especially when an application requires full access to your account. Other applications may be more specific about the permissions they need, limiting access only to the photos you select to share with them. Okay, I'm going to accept and grant access now. As you can see, Photobee can now access all my photos, allowing me to select which ones to edit without having to provide my username and password. Behind the scenes, an access token was generated and shared with the client, enabling it to fetch my photos and data from OneDrive. Let's check this together using Chrome DevTools. I will click on Inspect here, then switch to Application. The access token is likely stored in the local storage by Photobee. So I will click here, then on Photobee. And here we go. There is the OneDrive access token. This is what it looks like. That covers everything for now. It's important to remember that as the resource owner, you always have the option to revoke access for a previously granted client. The last point I want to demonstrate is how to revoke access. So here in my Microsoft Authorization Server settings, under Privacy, you will see App Access. Choose which apps and services can access my info. I will click on it. You will see Photobee listed here. And you can revoke access by clicking on Allow. Let's take a look at the details first. It says, you have given Photobee access to this information. Here is a brief summary of the permissions I granted Photobee. And now I can stop sharing and revoke access. That was everything for this demo. You can try this with most applications that require data from other cloud services. In the next lesson, we will explore the different OAuth 2 client types, so stay tuned. In this lesson, we are going to explore the two types of clients in OAuth 2. As we learned in previous lessons, an OAuth 2 client is an application that the resource owner grants access to their resources. When configuring your authorization server, you will need to define these applications as OAuth 2 clients within the server. At this point, you will need to decide whether you are configuring the application as a public client or a confidential client. Understanding this difference is essential to ensure a correct configuration in the authorization server and to avoid security misconfiguration vulnerabilities. Additionally, the client type you choose will also impact the OAuth 2 flow you will implement, which we will discuss in detail later. In simple terms, a public client is an application that cannot securely store secrets, while a confidential client is an application that can. You can think of the client secret as the password for the application. If the application cannot securely store this password, it falls into the public client category. Let's start with public clients. Public clients are typically applications that cannot securely store credentials, such as client secret. Examples include browser-based applications like single-page applications, native mobile applications, desktop applications, and even applications running on smart TVs. These applications operate in an environment where the user, not the application developer, has control. For instance, a single-page application loads everything in the browser, including the entire application code. This means that variables, entries, and any sensitive information defined within the application could potentially be exposed if not handled correctly. Similarly, mobile applications and applications on smart TVs also run on devices controlled by the user. This user-controlled environment means that credentials stored or used by these applications can be intercepted more easily. Frameworks like Vue.js, Angular, React, Swift for iOS, Android, and even some frameworks for smart TVs are examples of technologies used to build public clients. The key takeaway here is that because these applications are running on the user's device, they cannot be trusted to securely manage sensitive information like client secrets. Now let's talk about confidential clients. Confidential clients are different because they run on servers that the developer controls, allowing them to securely store and manage credentials. These are typically server-side applications such as traditional web applications or enterprise-level applications. Since these applications are hosted on a server which is controlled environment, they can securely store credentials like client secrets. This secure storage makes them much safer when interacting with the authorization server, as they can authenticate themselves effectively without exposing sensitive information. Frameworks like Laravel, Spring, Django, and Node.js are often used to build confidential clients, because they can securely handle sensitive data, for example as environment variables. So the key difference between these two client types lies in where they run and who controls the environment. Public clients run in environments controlled by the user, making them less secure and more prone to interception. Confidential clients, on the other hand, run in environments controlled by the developer, allowing for secure credentials management. In our next lesson, we will explore how OAuth 2 scopes help define what data an application can access and how they limit permissions to keep resources secure. In this lesson, we will explore the essentials for OAuth 2 scopes. We will start by understanding what scopes are and why they are crucial for controlling access to API resources. Then, we will discuss how to structure and name scopes effectively to ensure they are both granular and manageable. Finally, we will examine different methods for deriving the necessary scopes from a business perspective. Introduction to the OAuth 2 scopes. Let's start with our scenario involving Alex and Sam. Do you remember when the notary asked Alex to review and confirm the permissions he wanted to give Sam? The permissions were: Sam is allowed to rent you car on your behalf, Sam is allowed to sell you greenhouse on your behalf. This worked perfectly at the time, right? But then Sam decides now he wants to sell the blue house as well. So he goes back to the authorities with his notarized declaration and says, I want to sell Alex's blue house now. But this time, the authorities stop him, saying, you have a valid notarized declaration for renting the car and selling the greenhouse, but not for selling the blue house or selling the car. Renting the car, selling the greenhouse, selling the blue house, and selling the car, these are exactly the OAuth 2 scopes. So what are OAuth 2 scopes? OAuth 2 scopes are used to specify which resources a client is allowed to access. In our scenario, we have resources like car, house green, and house blue. Scopes are applied to these specific resources, ensuring that the client's access is restricted to only the resources they are permitted to interact with. In addition to defining resources, OAuth 2 scopes also specify the actions that can be performed on those resources. For instance, in our scenario, a client or Sam has permissions to rent a car or sell a greenhouse, but not to sell a blue house or a car. This clear separation of resources and actions allows for a fine-tuned access control, ensuring clients can only perform the actions they are explicitly permitted to. So scopes act as gatekeepers, defining exactly what a client is allowed to do within the API. This ensures that access is tightly controlled and clearly specified, providing a robust security mechanism. So why applying OAuth 2 scopes is crucial? By applying OAuth 2 scopes, we ensure that each client only has access to the resources and operations that are necessary for their role. This minimizes unnecessary access and helps maintain strict control over what each client can see or do within the system. The principle of least privilege is a cornerstone of security practices. By applying it through OAuth 2 scopes, we limit the permissions granted to clients, reducing the potential damage that could occur if their credentials were compromised. This makes systems more resilient to attacks. Now let's dive into how we can structure and name these scopes effectively to ensure they meet our security and business needs. OAuth 2 scope structure. Granular. Scopes should be detailed enough to control access to specific actions or resources without going overboard. For example, instead of having a broad products managed scope, you might break it down into products read and products write. This allows for precise control over what each user or application can do. Least privilege. Grant only the minimum permissions necessary for users or applications to complete their tasks. If a user only needs to view data, they should not be granted write access. This principle reduces the risk of misuse or security breaches. Scope explosion. But here you should be careful on the other hand. Avoid creating too many highly specific scopes that can overwhelm your access management. For instance, instead of creating separate scopes for every possible action, group them logically to simplify management and avoid confusion. Hierarchical scopes. Use a hierarchical naming convention to structure your scopes logically. For example, you might have a products scope with sub-scopes like products read and products write. This makes it easier to manage and understand permissions. Naming conventions and consistency. Business domain terminology. Ensure that the names of your scopes align with the business terminology. This makes it easier for both developers and stakeholders to understand what each scope does and how it relates to business operations. API alignment. Scopes should be directly aligned with your API structure. Each scope should correspond to specific API operations, like reading or writing data, ensuring that the scopes reflect what the API actually does. Consistent naming structure prefix. Follow a consistent naming pattern, like resource action, for example, orders read or products write. This consistency helps in understanding and manage the scopes across your API. Versioning. As your API evolves, you might need to update your scopes. Implement versioning like orders read v1 and orders read v2 to handle changes while maintaining backward compatibility. Meaningful documentation. For API developers and for users reviewing permissions. For API developers, provide detailed documentation for each scope explaining its purpose and how it should be used. This helps developers implement the scopes correctly and avoid misuse. For users reviewing permissions, make sure that your scope descriptions are user-friendly and explain what each scope does in simple terms. This helps users make informed decisions about the permissions that they grant. So now let's move on to exploring various methods for deriving these scopes. There are no hard and fast rules for defining OAuth scopes. It really depends on specific requirements and nature of the project. However, based on my experiences, I can share some valuable advices on how to approach this. When defining OAuth scopes, there are multiple approaches you can take. You might define scopes derived from the business processes, from the structure of your REST APIs, or based on access management methodologies like opaque, role-based access control in hierarchical organizations. Additionally, it's crucial to consider audit and compliance requirements. Often the best approach is to use a combination of these methods to create a comprehensive and effective scope strategy. Business-aligned scopes. One method is to derive scopes directly from the business processes. Scopes should reflect your business logic, aligning with core functions. For example, in an e-commerce platform, you could have scopes like orders view, products manage, and customers read. These clearly correspond to key business operations, making it obvious what each scope controls. REST APIs. Another approach is to align your scopes with your REST API structure. Each API endpoint, such as a get orders or post products, should correspond to a specific scope like orders read or products write. This method ensures that your access control is directly tied to the actions users can perform within the API. Role-based access control. You can also design scopes based on the roles within your organization, especially in hierarchical environments. For instance, an admin role might have access to all scopes, such as order read and products write, while a customer service role might be restricted to only orders read. This role-based approach ensures that users have the appropriate level of access based on their job functions. Audit and compliance requirements. Finally, consider audit and compliance requirements when defining your scopes. In some cases, you might need to separate actions like adding and updating products into different scopes to ensure that each action can be tracked and audited. However, it's important to balance this with the need to avoid unnecessary complexity. Sometimes a single scope with detailed logging may be more practical. In practice, you will often use a combination of these methods to define your scopes effectively. By considering business logic, API structure, role-based access control, and compliance needs, you can create a robust and flexible system for managing access through OAuth scopes. The last thing I want to mention in this lesson is a reference to our previous demo. If you remember, we saw through the URL that the OAuth client photo used the files read-write all scope to manage resources on the OneDrive resource server. Within Microsoft Graph, you can explore all the other scopes Microsoft defines to access resources from OneDrive. They also provide this important notice here. As a best practice, request the least privileged permissions that your application needs in order to access data and function correctly. Requesting permissions with more than the necessary privilege is poor security practice which may cause users to refrain from consenting and affect your application's usage. And if we scroll down here, we can explore all the scopes available to clients. If I search here for the scope that Photobee uses, files read-write all. So here we see it with the display text. Have full access to all files user can access. And the description that users see allows the app to read, create, update, and delete all files as assigned in user can access. That concludes our discussion on OAuth scopes. In the next lesson, we will briefly explore the differences between an OAuth access token and an OAuth refresh token. Stay tuned. This will be a simple and straightforward lesson where we will dive into what an OAuth access token is and how it differs from a refresh token. You may have already gotten a general idea of what an access token is through our previous lessons, but let's dig a bit deeper and explore some details. Remember in our scenario when the notary gave Alex the notarized declaration for Sam? This was a form of delegation, allowing Sam to perform specific actions on some of Alex's resources on his behalf. That notarized declaration acts similarly to an OAuth access token with the specific actions and resources described as scopes defined within the token. An access token is essentially a digital key that grants access to protected resources. It's composed of random characters, strings, and numbers. Access tokens can be either structured JWT tokens or unstructured opaque tokens. We'll explore the differences between these in the next lesson. This token is what allows third-party applications to access your data without you having to share your passwords directly. One of the key advantages of using access tokens is that they replace the need to send passwords with each request and to each third-party client, significantly enhancing security. Because of its crucial role, an access token must be stored securely due to its insensitive nature. It's crucial to ensure that unauthorized users and clients cannot access this token. An access token is typically short-lived, ranging from minutes to hours. This limited lifespan means that even if the token is compromised, the potential damage is minimized. Now let's see how an access token differs from a refresh token. Simply put, a refresh token is used to obtain new access tokens when the current access token has expired. Typically, when you fetch an access token from the authorization server, the server provides both an access token and a refresh token. If the current access token expires, you can use the refresh token to obtain a new access token and a new refresh token. The number of times you can refresh the access token depends on your configuration and security requirements. So, stepping back a little, when you use the refresh token to obtain a new access token, you send a POST request to the authorization server. So here's what this card command looks like. URL authorization server token. This is the URL of the authorization server, specifically pointing to the token endpoint. We include also a header with this content type to specify the format of the data in the request body. And the request body contains the following information: grant type refresh token. The term grant type refers to the method by which an application obtains an access token. In this case, we are specifying that we are using a refresh token to get a new access token. Refresh token. This is the actual refresh token that was issued previously, and it's now being used to request a new access token. Client ID. This is the client ID that uniquely identifies your application to the authorization server. Client secret. This is the client secret associated with the client ID used for authentication. Note that this could be optional if you are using a public client that does not require a client secret. If you remember from our lesson on client types, public clients cannot securely store credentials like the client secret. So, the main purpose of a refresh token is to obtain a new access token when the current ones expire. Think of it as a key that allows you to keep your session active without needing to re-authenticate every time. By using refresh tokens, OAuth 2 enables the use of short-lived access tokens. This approach significantly reduces the risk if an access token is compromised, because the attacker only has a limited time to use it before it expires. Like access tokens and other credentials, the refresh token must be stored securely due to its sensitive nature. It's crucial to ensure that unauthorized users and clients cannot access this token. Another key difference between refresh tokens and access tokens is their lifespan. Refresh tokens typically have a longer lifespan than access tokens. While access tokens might be short-lived, lasting minutes to hours, refresh tokens can last much longer, sometimes days or even weeks, depending on the configuration and the scenario. Now that we have covered what an access token is and what a refresh token is, in the next lesson we are going to explore two formats that are commonly used in the OAuth 2 context: the structured JSON Web Token and the unstructured opaque token. In the last lesson, we explored what an OAuth 2 access token is and how it functions. Now let's take a closer look at how these tokens are structured, specifically the formats they come in. The two most common formats in this context are the structured JSON Web Token, JWT, and the unstructured opaque token. In simple terms, an opaque token is a random string of characters that does not reveal any information about its contents, while a structured JWT token does. A JWT contains data in a format that's readable and can be decoded. Let's start with the opaque token. This type of token is essentially a random string of characters and does not reveal any information on its own. Hence, it's called opaque. You cannot look at an opaque token and understand what it represents because it's not readable or decodable by just looking at it. Because an opaque token does not carry any inherent information, the resource server which receives the token does not automatically know whether it is valid or not. This means the resource server requires server-side validation. The resource server must send a request to the authorization server to validate the token and determine its legitimacy. In practice, when a client presents an opaque token to a resource server, the server has to make an additional call to the authorization server to validate the token and retrieve any relevant information. The key advantage of opaque token is their high level of security. Since the token doesn't expose any information directly, it offers a strong protection, especially in scenarios where token exposure is a significant concern. However, a notable drawback of opaque token is the need for constant server-side validation. These requirements can introduce latency and additional overhead, as the resource server must make frequent calls to the authorization server to validate each token, potentially impacting performance in high-traffic scenarios. Now let's move on to the structured JSON Web Token, or JWT for short. A JWT is a structured token format which written in JSON, JavaScript object notation, which means it's not just a random string of characters. Instead, it's a token that actually contains information about the user and the permissions granted. Let's break down the structure of a JSON Web Token, JWT. A JWT is composed of three main parts: the header, the payload, and the signature. The header typically contains two pieces of information: the type of token, which is a JWT, and the signing algorithm being used, such as RS-256. The header might also include a key identifier, KID, which is used to select the key was used to sign the token. The payload is the part of the JWT that contains the claims. Claims are statements about an entity, typically the user, and additional metadata. For example, in this payload we have the issuer of the token indicating who issued it, like the URL of the authorization server that issued the token, And the subject of the token, usually a user ID. Audience, the audience for whom the token is intended, often specific API, and the expiration time indicating when the token should no longer be accepted. Times in JWT tokens are usually in numeric data formats. Issued at, the time when the token was issued, and JWT ID, a unique identifier for the token. Authorized party, the party or OAuth 2 client to which the token was issued. Scope, the permissions, resources, actions associated with the token, like orders read. Roles, the roles assigned to the user, for example, an opaque role in a hierarchical organization such as a user or admin. Signature, the signature verifies the authenticity of the token and prevents its alteration. It ensures that the information within the token has not been tampered with or changed. In other words, the signature validates the authenticity of the data, confirming that the token was indeed issued by the proper authority and that its content are trustworthy. The information contained within the JWT is base 64 encoded. So while you can easily decode it and read the contents, it's not encrypted by default. This means that anyone who gets hold of the token can see what is inside. So it's important to ensure that sensitive information is not exposed in the token unless it's probably encrypted. Here is an example of decoded JWT token. It consists of three parts: the decoded header in pink, the decoded payload in purple, and the signature in cyan, that can be validated locally by the resource server. These three parts are concatenated by periods. Because the JWT includes essential token validation details such as the expiration time and a signature, along with the key information in the header, the resource server can validate the token locally without needing to send validation requests to the authorization server. This local validation can make the process more efficient. Self-contained data. Unlike opaque tokens, JWTs carry the information they need to operate within the token itself. This includes details like the user's identity, the permissions granted, and the token's expiration time. You can decide which information to include based on your security requirements. For example, you can include details like an employee's role, an ID, but omit personal data. However, one downside is that if the token is not properly encrypted, sensitive data could be exposed. Therefore, while JWTs offer convenience, they require carefully handling to maintain security. Let's recap everything we have covered so far. We have discussed two key formats of OAuth to access tokens: opaque tokens and JWT tokens. Structure. Opaque tokens are unstructured and do not carry any readable information with them. JWT tokens, on the other hand, are structured with three parts: header, payload, and signature, making them self-contained and descriptive. Readability. Opaque tokens are not human readable, making them more secure in that their contents cannot be directly understood. JWT tokens are human readable unless encrypted, meaning their contents can be decoded and understood, which can be both an advantage and a risk, depending on how they are used. Introspection. Opaque tokens require introspection, meaning the resource server has to ask the authorization server whether the token is valid and retrieve any relevant information. JWT tokens don't require introspection as they are self-descriptive. The resource server can validate the token and its contents locally. Self-content. Opaque tokens are not self-content. They rely on external validation and storage to function. JWT tokens, however, are self-content, carrying all the necessary information within the token itself. Integrity and authenticity. Opaque tokens don't inherently provide any integrity or authenticity. That's handled by the server-side validation. JWT tokens come with a signature that ensures the integrity and authenticity of the token, making them more versatile for local validation. Standard and custom claims. Opaque tokens don't typically include claims directly within them. JWT tokens can include standard or custom claims like subject or expiration, making them more flexible in their use. To wrap up, we touched on two important concepts: introspection and self-validation. But what exactly is introspection and how does it differ from self-validation? And how does self-validation actually work? These are questions we'll dive into in detail in the next lesson. Stay tuned. Now let's dive into the two methods used for validating an OAuth 2 access token: token introspection and local token validation. As we learned in our last lesson, token introspection requires server-side validation from the authorization server, which works for both opaque tokens and JWT tokens. On the other hand, local validation is applicable only to JWT tokens, since they are self-contained and can be validated locally. In simple terms, token introspection is an online real-time validation method that involves querying the authorization server to check the validity of a token, while a local validation is an offline method that can be performed directly by the resource server using the integrity and authenticity of the token itself. Let's start with token introspection because it's similar to understand. In this scenario, we have the OAuth 2 client, the resource server, and the authorization server. The client uses an OAuth 2 access token to authorize itself on the resource server to access resources or perform specific actions. The token used here can be either an opaque token or a JWT token. When the resource server receives the token, it sends a validation request with the token to the OAuth 2 introspect endpoint on the authorization server to determine whether the token is valid. The authorization server then validates the token and sends back a response indicating whether it is valid or not. Now let's take a step back and look at how this request is constructed. You have a post request that points to the OAuth 2 introspect endpoint on the authorization server. The only required parameter in the request body is the token, which is the token to introspect. If you want to enhance the lookup process in the authorization server, you might also include the optional parameter token type hint, where you can provide a hint about the type of the token being submitted for introspection. To further enhance security, the resource server can also be defined as an OAuth 2 client in the authorization server. This means including its client ID and the client secret credentials to authenticate itself as well. The response from the authorization server could be as simple as 200 OK, active true, or if the token is not valid, active false. Alternatively, the response could include more detailed information depending on the configuration of the authorization server. Here is an example. In this more detailed response, you can see information such as scopes, username, user ID, and more. Now, let's take a closer look at how local token validation actually works. As we have learned in previous lessons, local token validation is possible with JWTs because they are self-contained tokens that include a signature. This is the third part of the JWT token. The signature plays a critical role in ensuring the integrity and authenticity of the token, meaning it confirms that no one has tampered with the token's validation information. So the real key to local token validation lies in understanding how this signature works. Once we grasp this mechanism, we'll have a solid understanding of how self-token validation functions. In general, there are two types of signing algorithms used to create these signatures: symmetric signing and asymmetric signing. In simple terms, symmetric signing involves a single shared secret key that's used by both the sender and the receiver. The same key is used to sign and verify the data, which means it must be kept secure by both parties. On the other hand, asymmetric signing uses two keys, a private key and a public key. The private key is kept secret and is used by the sender to sign the data. The public key, which is available to anyone, is used by the receiver to verify the signature. Let's start with the symmetric signing approach. Imagine a scenario with Bob and Alice. Bob and Alice often message each other, but they want to ensure that their messages are not tampered with by an evil guy who wants to cause trouble in their relationship. To protect their messages, Alice and Bob share a secret key called a shared secret. This key must be kept secure by both of them. Now, Bob writes a message to Alice, "Hi Alice, I miss you," and then signs it using the shared secret key. This signature allows Alice to verify the integrity and authenticity of the message, ensuring that the evil guy hasn't tampered with it. When Alice receives the message, she uses the same shared secret key to verify the signature. And there we go, she can now be sure that the message truly came from Bob. Now let's relate this scenario to a JWT access token. In this analogy, Bob represents the OAuth 2 authorization server, which has a shared secret key. The message is like the JWT token that authorization server creates and signs with the shared secret before sending it to Alice. Alice in this case is the resource server. She receives the token via the OAuth 2 client and needs to verify its signature locally using the same shared secret key. Now imagine the evil guy as a man-in-the-middle attacker who tries to manipulate information in the JWT token, for example changing the scope from orders read to orders write. Unfortunately for him, the resource server catches this during the local signature validation process, which ensures the token's integrity. The verification fails because the information no longer matches the original signature. The evil guy would need to re-sign the token with a new signature that aligns with the altered information. But he doesn't have the shared secret, which makes him very sad. We mentioned earlier that the shared secret must be kept secure, but here we encounter a significant problem. The authorization server often doesn't trust the client applications, and for good security practice it should not. When there are multiple clients, let's say 100, sharing the same shared secret for token verification can pose a serious security risk. This is why asymmetric signing of tokens is commonly the safer solution, as it allows each client to verify the token without exposing the critical secret. But how does asymmetric signing work exactly? Asymmetric signing is based on two keys, a private key and a public key. In this scenario, Bob, who writes the message, has a private key, while Alice, who receives the message, has a public key. The public key is publicly available for anyone or any client that wants to verify that the message truly comes from Bob. However, the private key must be kept secure. Similar to the previous scenario, Bob writes a message to Alice. "Hi Alice, I miss you," and signs it with a private key. The signature allows Alice to verify the integrity and authenticity of the message, ensuring that the evil guy hasn't tampered with it. When Alice receives the message, she uses now the public key to verify the signature. And there we go, she can now be sure that the message truly came from Bob without needing to get the private key that signs the information. Bob represents the OAuth 2 authorization server, which has the private key. The message is like the JWT token that the authorization server creates and signs with the private key before sending it to Alice. Alice is the resource server. She receives the token via the OAuth 2 client and needs to verify its signature locally using the public key. This public key could be stored in each resource server that needs to validate the tokens. Alternatively, the authorization server could provide an endpoint that allows resource servers to fetch the public key as needed. This approach is more practical because if the authorization server changes its public key, the resource server can automatically fetch the updated key from the endpoint. In many frameworks like Spring Boot with Spring Security, the key will be cached when the application starts. And if unknown signature is countered, the application will call the endpoint again to update the public key if necessary. Now, the evil guy, the man-in-the-middle attacker, tries again to manipulate the information in the JWT token. For example, changing the scope from orders read to orders write. The verification fails again because the information no longer matches the original signature. The evil guy would need to re-sign the token with a new signature that aligns with the altered information. But he doesn't have Bob's private key. Even if he has the public key, he can only verify messages but not sign them. That's why even if we have 100 OAuth 2 clients, each with a public key, we ensure that only our trusted authorization server can sign the tokens. That's why we use the asymmetric signing method for signing OAuth 2 access tokens. The resource servers need only the public key to validate the JWT token, where the authorization server is the only party that possesses the private key used for signing the tokens. Let's recap the two methods of token validation by comparing introspection and local self-validation across key aspects. Token type. Introspection supports both opaque tokens and structured tokens. Local self-validation typically limited to structured tokens like JWTs, as the token itself must contain all necessary information for validation. Connection to authorization server. Introspection requires a connection to the authorization server. The resource server must communicate with the authorization server for token validation, preventing it from operating independently. Local self-validation doesn't require a connection to the authorization server, as the token carries all the information needed for validation. This allows the resource server to operate autonomously without relying on the authorization server. Real-time status. Introspection can provide real-time information on the token's status, such as whether it has been revoked. This makes it highly useful in situations where real-time validation is critical. Local self-validation cannot check the current status of the token because it is stateless. Once a token is issued, its status remains unchanged unless the resource server queries the authorization server again. Network load and latency. Introspection typically results in a higher network load and latency, as each token validation requires a request to the authorization server. This can increase latency, especially in high-traffic environments. Local self-validation more efficient as no external requests are needed. The validation process is faster, leading to lower latency overall. Depth of information. Introspection can provide detailed token information, since the authorization server holds all the details. This allows for more comprehensive data about the token, its owner, and its permissions. Local self-validation limited to the information contained within the token itself. The resource server only has access to the data encoded in the JWT. Scalability. Introspection, centralized validation can slow things down, especially in environments with a high volume of validation requests. Local self-validation scales well, as it doesn't rely on external dependencies. Each resource server can validate tokens independently, making it more suitable for large distributed systems. Use cases. Introspection, ideal for scenarios involving opaque tokens or when real-time status updates such as token revocation are critical. This method is particularly useful when immediate token invalidation is necessary to maintain security. Local self-validation best suited for applications that require autonomous operation and utilize self-descriptive tokens like JWTs. This approach is especially beneficial in distributed systems where low latency and high scalability are key priorities. To wrap up everything, introspection is a reliable method when working with opaque tokens or in scenarios requiring real-time validation and detailed token information. However, it can introduce additional network load and latency due to continuous communication with the authorization server. Local self-validation, on the other hand, offers greater efficiency and scalability, making it a strong choice for distributed systems despite the lack of real-time status updates. The typically short lifespan of JWT access tokens, often just a few minutes, helps reduce the risk of using an outdated or compromised token. However, if your use case cannot tolerate even this brief time window, introspection remains necessary even when using JWTs. In this lesson, we'll introduce OpenID Connect protocol and see how it builds on OAuth 2 to provide seamless user authentication and identity management. We'll start with a brief introduction to what OpenID Connect is, then move on to a comprehensive comparison between OpenID Connect and OAuth 2. And finally, we will wrap up with a practical scenario to see OpenID Connect in action. Let's start by understanding what OpenID Connect really is. Let's see how the OAuth 2 team defines it. OpenID Connect is an identity layer built on top of the OAuth 2 framework. It allows third-party applications to verify the identity of the end user and obtain basic user profile information. OpenID Connect uses JSON Web Tokens, JWTs, which you can obtain using flows, conforming to the OAuth 2 specifications. An identity layer built on top of the OAuth 2 framework. So let's imagine OAuth 2 and OpenID Connect as layers of a cake. This means the first layer or the foundation is OAuth 2, which provides the groundwork for everything that comes next. The second layer, OpenID Connect, is built on top of this foundation, adding identity-related capabilities. So OpenID Connect essentially equals OAuth 2 plus some additional features or extensions. These extensions are what enable OpenID Connect to verify user identities and provide basic profile information. Now let's explore how OpenID Connect differs from OAuth 2 by examining several key aspects. Primary function. OAuth 2 focuses on access control for resources, handling authorization by delegating authority to third-party services, while OpenID Connect builds on this by adding an identity layer, combining both authorization and authentication. OpenID Connect is essentially OAuth 2 plus identity extensions. Resource owner identifier. OAuth 2 doesn't provide an identifier for the client to recognize the resource owner by default, whereas OpenID Connect does. It provides the client with information about the user, allowing for user identification. Token issued. OAuth 2 issues access tokens and refresh tokens, while OpenID Connect extends this by also issuing an ID token specifically designed to convey the identity of the user. Token type. OAuth 2 allows for tokens that can be either opaque or JWT tokens, whereas OpenID Connect requires the ID token to be in JWT format, ensuring that the token is structured and can securely carry user information. User information access. OAuth 2 lacks a standardized method for accessing user information, while OpenID Connect provides a user info endpoint, which is a standardized way to retrieve user profile information. Scopes. OAuth 2 doesn't require specific scopes by default, whereas OpenID Connect mandates the OpenID scope to indicate that the client is using OpenID Connect and expects identity-related information. Flow types. OAuth 2 supports both user-initiated flows and machine-to-machine flows. In contrast, OpenID Connect is primarily for user-initiated flows, focusing on user authentication and identity, making it unsuitable for machine-to-machine scenarios. Now let's see the differences in a practical flow in action. As I mentioned earlier, OpenID Connect builds on OAuth 2, so we use the same OAuth 2 roles and flows, but with some added extensions. One key extension in OpenID Connect is the addition of a user info endpoint on the authorization server. This endpoint is specifically used for retrieving detailed user profile information. As usual in the standard OAuth 2 flow, the resource owner initiates the process by wanting to log in into an application. Since the resource owner never directly gives his credentials to the client or to the third-party application, he is redirected to the OAuth 2 authorization server. This is similar to how we were redirected to Microsoft for OneDrive access in the FOTB demo. The resource owner enters his credentials and authenticates himself at the authorization server. Afterward, he reviews the scopes or permissions being requested and confirms if everything looks good. It is important to note that in an OpenID Connect flow, the scopes include identity-related information such as the user's profile, email, or other personal details. After the user has authenticated and confirmed the requested scopes, the authorization server will typically generate 2 or 3 tokens. The first is an ID token, which contains information about the user's identity and is always in JWT format. The second is an access token, which the client can use to access protected resources or call the user info endpoint for more detailed user information. Additionally, a refresh token might also be issued if the client needs to maintain access beyond the lifespan of the access token. If the client application requires more detailed user information, it can use the access token to call the OpenID Connect user info endpoint. This endpoint can provide additional identity details like personal data, birth date, website, profile picture, and private address. The reason the client uses the access token and not the ID token for the user info endpoint is because the access token is designed to authorize specific actions and requests on behalf of the user, whereas the ID token is primarily meant for identity verification. The last thing I want to mention is, if you remember the last demo with FOTB, I will be using FOTB again, but this time instead of granting access to my data from Microsoft OneDrive, I will be authenticating myself through my Microsoft account using OpenID Connect and OAuth 2. So here I am in FOTB again. I will click on account and then log in. So as you see, there are 4 different methods or identity providers that use OpenID Connect to authenticate myself. I'll go with Microsoft again and click on Login with Microsoft. Now I have been redirected to Microsoft's login page where I need to enter my username and password. Notice that in the URL there is a different scope now required compared to the last demo where we accessed data. This time the scope is user read. Last time it was something like files, read, write, all for full access to files. So I'll enter my credentials again. Now I am asked to review the scopes or permissions I am granting to FOTB. These are identity-related permissions now. FOTB needs your permission to read your profile. FOTB will be able to read your profile. Okay, I'm going to accept this. And here we go. I am now logged in. And as you see, FOTB has some of my identity information now, like my first name and last name. In this chapter, we'll dive deep into all the user-initiated flows in OAuth 2, exploring scenarios where the user actively participates and initiates the flow. We will cover what they are, how they work, the challenges associated with each, and most importantly, when to use each flow. We'll begin with the implicit flow, which is the simplest OAuth 2 flow and serves as a foundation for more complex flows to come. We'll break it down by examining the OAuth 2 roles involved, the types of clients and applications it supports, and the specific endpoints utilized. Starting from the user initiation point, we'll go through the flow step by step, exploring the requests, required and optional parameters, and how they are structured in curl commands. We'll also discuss where scopes come into play and track the flow through access token validation on the resource server. To wrap it up, we will consolidate everything in a sequence diagram that illustrates the entire flow. Then we'll uncover the security challenges of the implicit flow through a real-world scenario involving a hacker intercepting the authorization process. This sets the stage for introducing the authorization code flow, which addresses those security risks. In the authorization code flow, we'll once again look at the OAuth 2 roles, the types of clients and applications it supports, and the endpoints involved. We will go through the flow step by step, detailing the requests and curl commands. And we'll compare how this flow differs from the implicit flow. We'll explore the tokens it supports and see how it successfully resolves the security issues present in the implicit flow, all the way to token validation in the resource server. We will then consolidate the steps in a sequence diagram and revisit the hacker scenario to see how the authorization code flow resolves the previous security challenges. But even here, there are still some potential vulnerabilities which we'll explore through another malicious application scenario, setting the stage for the next flow. Finally, we will dive into the PKCE flow, proof key for code exchange. We will explore what PKCE is, how it works, and which clients and applications it's suitable for. Walking through the flow in a step-by-step sequence diagram, we will see how PKCE specifically tackles the security issues found in the authorization code flow. At the end of this chapter, we will recap all three flows: implicit, authorization code, and PKCE in a comprehensive overview. We'll conclude with a decision tree that guides you in determining when to use each flow and for which applications. We'll walk through the decision tree step by step, considering various requirements, environments, and the project situations to help ensure that your architectural decisions are aligned with the right security measures for your use case. Let's start with the implicit flow, the simplest of the user-initiated OAuth 2 flows. It's very similar to the standard OAuth 2 flow we covered in the last chapter, but with some deeper technical details. First, we have the familiar OAuth 2 roles: the resource owner, the client, the authorization server, and the resource server. The authorization server has a specific endpoint called the authorize endpoint. This is where the resource owner is prompted to authenticate. The implicit flow is designed specifically for browser-based applications that run directly in the browser, like Google Chrome or Firefox. Because these are public-facing applications, the OAuth 2 client must be configured as a public client in the authorization server. If you remember from the last chapter, a public client is an application that cannot securely store sensitive credentials like client secrets. The authorization server presents a user interface, a login screen where the resource owner is redirected when interacting with the client. This UI is part of the authorize endpoint. In most authorization servers, you can customize this interface to align with your organization's branding or theming requirements. The process begins with the resource owner initiates the flow, either by clicking login or granting the client access to the resources. As we have discussed, the resource owner never shares their credentials directly with the third-party applications. Instead, the client redirects them to the authorization server's authorize endpoint where they enter their credentials. This redirect typically happens via an HTTP 302 request. The URL for this request contains several important query parameters. Client ID, this identifies the client application requesting access on behalf of the user. Response type equals token. This tells the authorization server that the client expects an access token in the response, indicating the use of the implicit flow. You might remember from the Photobe demo when the application redirected me to Microsoft's authorization server. Response type equals token indicated that Photobe was using the implicit flow. Redirect URI. This specifies where the authorization server should redirect the resource owner after successful authentication. For security reasons, these URIs must be pre-registered in the authorization server, either as an approved list or using regular expressions like wildcard.example.com. These three parameters, client ID, response type equals token, and redirect URI, are required for the implicit flow. There are also two optional but highly recommended parameters. Scope, this limits the access or actions the client can perform in the API, such as orders read. State, a random string used to maintain state between the request and callback, which also helps protect against CSRF attacks. Again, referring back to the FOTB demo, the request URL had a similar structure. The authorized endpoint, and the query parameters like client ID, scope, response type equals token, and redirect URI. So the resource owner now enters his credentials like an email and password into the authorization server. The authorization server verifies the credentials, ensuring everything is correct. Once verified, the authorization server shows the resource owner the requested permissions scopes in a user-friendly description and asks the user to review and confirm them. For example, in the FOTB demo, I was asked by Microsoft to review and confirm the permissions scopes that FOTB needed to access my data in OneDrive. Note that while this step is highly recommended for security purposes, it's still optional and can be configured based on your business needs and requirements. If everything looks good and the user approves, the authorization server generates an access token and redirects the resource owner back to the client's redirect URI specified in the initial request. The response is sent as a URL with a fragment identifier containing the access token and other relevant data, like the token type and expiration time, all within the URL. After the fragment identifier, you will see the access token type, for example bearer, which means the token can be used by anyone who holds it to access the resources, and expires in 3600 seconds, meaning the token will expire in 1 hour. The response also includes the state value, which should match the state value in the initial request. This is used to prevent CSRF attacks by ensuring the integrity of the transaction. After receiving the access token, the client can now use it to authorize its request when accessing user data or performing actions on behalf of the resource owner by presenting this access token. The resource server then validates and verifies the access token either locally or by making a request to the introspection endpoint of the authorization server. We have covered both mechanisms, local validation and introspection, in the token validation lesson. If the token is successfully verified, the resource server provides the requested resources to the client, completing the process. Now let's recap everything by walking through the following sequence diagram. We have the key players, the resource owner, the browser where the client runs, the client application itself, the authorization server where the client is registered as a public client, and the resource server. The resource owner initiates the request by wanting to log in. The client redirects the resource owner via the browser to the authorization server with this redirect request. Note that the response type must be set to token, indicating that the implicit flow is being used. The resource owner authenticates with the authorization server, and if applicable, reviews and approves the requested scopes. After successful authentication, the authorization server creates an access token, packages it into the redirect URI as a URI fragment identifier along with additional parameters, and redirects the resource owner back to the client through the browser. The client then uses the access token to access resources on behalf of the resource owner from the resource server. Finally, the resource server verifies the access token and, if valid, provides the requested resources to the client. Up until now, everything seems perfect, right? However, if we take a closer look at the response URI and see how the access token is passed to the client as a fragment identifier in the URI, we notice a serious risk. Access tokens in URIs are vulnerable to attacks. For example, an attacker could obtain an access token by intercepting browser history or network traffic. Let's understand this risk better by going through the following short scenario. Imagine we have a malicious application, an interceptor, that's capable of intercepting browser or network traffic. This application could have been installed without users' knowledge in various ways, for instance through phishing attacks such as clicking on a malicious link in an email or by exploiting vulnerabilities in public Wi-Fi networks. When the authorization server returns the access token in the URI via the browser, the malicious application could intercept it because it's monitoring the traffic. Then the malicious application uses the intercepted token to request resources from the resource server. The resource server verifies the token, and here we go, the token is valid and the hacker gains access to the resources. But he should not have access, which makes the resource owner very sad. This is precisely why the implicit flow is deprecated in OAuth 2.1. But this doesn't mean that no one should use it anymore. There are still scenarios where it may be suitable, and as we saw in the FOTB demo, FOTB used the implicit flow. We'll cover the possible use cases at the end of this chapter, where I will present a short comprehensive comparison between the different flows, exploring the scenarios each flow is suited for, and introducing a decision tree to help guide you on when to use which flow. But for now, the more interesting part is how the authorization code flow solves the security challenge by modifying some key steps of the implicit flow. First, I want to highlight that in general, the PKCE flow is an extension of the authorization code flow. However, for clarity and to distinguish the concepts and use cases of each, I am treating these flows as two separate flows in this course. So whenever I mention the authorization code flow, I am explicitly excluding the PKCE flow. Now let's dive into the authorization code flow. As always, we start with the familiar OAuth 2 roles: the resource owner, the client, the authorization server, and the resource server. In all user-initiated flows, we make use of the standard OAuth 2 authorized endpoint. This is the endpoint that provides a login screen where the resource owner is redirected when interacting with the client to enter their credentials. However, in this flow, we also use another standard OAuth 2 endpoint, the token endpoint. The token endpoint is where the client exchanges an authorization code for an access token. Unlike the implicit flow, where only browser-based applications are used, in this authorization code flow, we have a broader concept of a user agent. However, the requirement is that the client must be a confidential client, meaning it can securely store sensitive credentials like client secrets. This makes the authorization code flow suitable for regular web applications and the traditional server-side applications where client credentials can be stored securely. Similar to the implicit flow, the process begins with the resource owner initiates the flow, either by clicking login or granting the client access to their resources. As we have discussed, the resource owner never shares their credentials directly with the third-party applications. Instead, the client redirects them to the authorization server's authorized endpoint where they authenticate. This redirect typically happens via an HTTP 302 request. The URL for this request contains several important query parameters. Client ID. This identifies the client application that is requesting access on behalf of the resource owner. Response type equals code. This is the key difference from the implicit flow. Instead of requesting an access token directly, the client is asking for an authorization code. That's why it's called the authorization code flow. The code is later exchanged for an access token. Redirect URI. This is where the authorization server should send the resource owner after successful authentication. For security reasons again, this URI must be pre-registered with the authorization server either as an approved list or using regular expressions like wildcardexample.com. These three parameters, client ID, response type equals code, and redirect URI are required for the authorization code flow. Like in the implicit flow, there are also two optional but highly recommended parameters. Scope. This limits the actions a client can perform in the API, such as orders read. State. A random string that helps maintain state between the request and callback, which also protects against CSRF attacks. So the resource owner now enters his credentials such as an email and password into the authorization server. The authorization server then verifies these credentials to ensure everything is correct. Once verified, the authorization server presents the requested permissions scopes in a user-friendly format, asking the resource owner to review and confirm them. If everything looks good and the user approves, the authorization server generates an authorization code instead of an access token as in the implicit flow and redirects the resource owner back to the client's redirect URI specified in the initial request. The response from the authorization server contains the location URL, which includes the authorization code and the state as query parameters. The authorization code is what the client will use to exchange for an access token, while the state parameter must match the original state value in the request, helping to prevent CSRF attacks by ensuring transaction integrity. Now, the client sends a POST request to the authorization server, specifically to the OAuth 2 token endpoint, presenting its credentials, client ID, and the client secret to authenticate itself as a machine. The POST request has the following key details. Content type is set to URL encoded form data. The authorization code is provided to be exchanged for an access token. The client credentials, client ID, and the client secret are included for authentication. The redirect URI must match the redirect URI specified in the original request to the authorized endpoint, ensuring consistency. Finally, the grant type is set to authorization code, indicating the client is using an authorization code to request an access token. You might remember in the refresh token lesson, the grant type was set to refresh token for requesting an access token via a refresh token. After sending the request, the authorization server verifies the client ID, client secret, and the authorization code. If everything checks out, the authorization server exchanges the code for an access token, and possibly a refresh token as well depending on the server configuration. It's important to note here that if the authorization code was intercepted during the user's interaction with the client, similar to how the access token could be compromised in the Implicit flow, the hacker would not be able to exchange the code for an access token. This is because they will need the client secret, which is securely stored by the client. When the client receives the access token, it can now use it to authorize its request when accessing the resource owner's data or performing actions on their behalf by presenting this access token. The resource server then validates and verifies the access token either locally or by querying the introspection endpoint of the authorization server. We have already covered both mechanisms, local validation and introspection, in the token validation lesson. If the token verification is successful, the resource server provides the requested resources to the client, completing the process. Now let's recap everything by walking through the sequence diagram of the authorization code flow. We have the same key players, the resource owner, the user agent, the client application itself, the authorization server where the client is registered as a confidential client, and the resource server. The resource owner initiates the flow by attempting to log in or by giving permission for the client to access their resources. The client then redirects the resource owner via the user agent to the authorization server's authorized endpoint with a redirect request. Note that here the response type must be set to code, indicating the authorization code flow is being used. The resource owner authenticates with the authorization server and, if applicable, reviews and approves the requested scopes. After successful authentication, the authorization server generates an authorization code and redirects the resource owner back to the client via the user agent, along with the authorization code and the state as query parameters in the URL. The client now needs to exchange the authorization code for an access token. To do this, it sends a POST request to the token endpoint of the authorization server. In this request, the client provides the authorization code, its client ID, and its client secret for the authentication. The redirect URI is also included to ensure it matches the one sent in the initial authorization request. Lastly, the client specifies the grant type equals authorization code, indicating it's using the authorization code to get an access token. The authorization server validates the authorization code and client credentials, client ID, and client secret. If everything is valid, the server responds with an access token and possibly a refresh token depending on the server configuration. A key difference from the Implicit flow is that the client sends the authorization code and client secret securely through a POST request, which is encrypted by TLS and receives the tokens securely. In contrast, the Implicit flow sends the access token in plain text via the URL. Finally, the client uses the access token to access resources on behalf of the resource owner from the resource server. The resource server validates the access token and, if valid, provides the requested resources to the client, completing the flow. Now let's see how the authorization code flow solves the security challenge of the Implicit flow that we covered in the last lesson. Once again, we have the same malicious application, an interceptor that's capable of monitoring and intercepting browser or network traffic. At the same point in the flow, when the authorization server redirects the resource owner back to the client via the user agent, instead of providing the access token directly in the URL as in the Implicit flow, it provides an authorization code. Now here the malicious application will intercept it again because it's monitoring the traffic. Then, the malicious application uses the intercepted code and sends a POST request to exchange the code for an access token. The authorization server will then validate the code and client secret equals I don't know. Since the client secret is incorrect, the request will fail and return an unauthorized response, which makes the hacker very sad. On the other hand, the legitimate client sends the correct POST request with the authorization code and its valid client secret. Client secret equals I know it. And there we go, the authorization server successfully verifies the request and grants the client an access token. This additional layer of security, the requirement of the client secret, prevents unauthorized access, solving the major security risk of the Implicit flow. Up until now, everything seems perfect, right? But let's see what happens if the client is a public client, like a single page application, which cannot securely handle secrets because it runs entirely in the browser. So the user agent is now a browser and the client is a single page application. Let's explore the following scenario. As we learned in the client types lesson, a single page application loads everything in the browser, including the entire application code. This means that variables, entries, and any sensitive information defined within the application could potentially be exposed if not handled correctly. The malicious application takes advantage of this vulnerability by using certain tools to obtain the client secret. Client secret, I know it. At the same point in the flow, when the authorization server redirects the resource owner back to the client via the browser, the hacker intercepts again the authorization code. Since they already have the correct client secret, I know it, they send both the code and the secret to the authorization server. And there we go, the verification succeeds, and the hacker is granted an access token, leaving the resource owner very sad. Single-page applications, also known as browser-based applications, run entirely in the browser after loading the JavaScript and HTML source code from a web page. Since the entire source is available to the browser, they cannot maintain the confidentiality of the client secret, so a secret is not used for these applications. So the implicit flow is insecure and deprecated, and the authorization code flow is suitable only for confidential clients. So how can we secure public clients? In the next lesson, we'll explore how the PKCE flow proof key for code exchange addresses this exact security challenge by extending the authorization code flow. Let's dive into the PKCE flow proof key for code exchange flow. As mentioned in the last lesson, PKCE is an extension of the authorization code flow. So essentially we have the same flow as before, but with an additional layer of security, the proof key for code exchange. But what exactly is this proof key for code exchange? The OAuth 2 client starts by generating a random string, which ranges between 43 and 128 characters. Next, the client hashes the string using a hash algorithm. The recommended standard for PKCE is SHA-256. This process results in a hash value. Afterward, the client encodes this hash value, giving us an encoded hash value. In PKCE, the random string is called the code verifier. The encoded hash value is called the code challenge, and the hashing algorithm used is called the code challenge method. If we have the code verifier and the code challenge method, we can generate the code challenge. And this is exactly the core of PKCE, the proof key for code exchange. It's important to note that PKCE supports a blame method without hashing. In this case, the code challenge is simply the same as code verifier. Although this method is less secure and typically discouraged, it exists for legacy clients or for situations where hashing is not possible. Now let's explore how the PKCE flow works. Since we already have a solid understanding of the authorization code flow, we can jump directly into the sequence diagram and see how the PKCE flow adds security. We have the same familiar players: the resource owner, the user agent, the client application, the authorization server, and the resource server. The cool thing about PKCE is that it supports both public clients and confidential clients. This makes it suitable for a wide range of applications, including browser-based applications, native mobile applications, desktop applications, and even traditional server-side applications. The resource owner initiates the flow by attempting to log in or granting permission to the client for accessing the resources. The client generates a PKCE, which includes the code verifier and code challenge. It stores the code verifier locally in memory or another secure location. The client then redirects the resource owner to the authorization server's authorized endpoint, similar to the standard authorization code flow. However, here is the key difference. In addition to the standard query parameters like client ID, response type, code, and redirect URI, the client also includes the code challenge and code challenge method in the request. The authorization server stores the code challenge and code challenge method. The resource owner authenticates with the authorization server and, if applicable, reviews and approves the requested scopes. After successful authentication, the authorization server generates an authorization code and redirects the resource owner back to the client, along with the authorization code and state as query parameters in the URL, just like in the regular authorization code flow. The client sends now a post request to the token endpoint of the authorization server to exchange the authorization code for an access token. There are here two key differences compared to the authorization code flow. The first key difference is that in the PKCE flow, sending the client credentials such as the client secret is optional for public clients, but required for confidential clients. The second key difference is that the client also includes the code verifier that was generated and stored earlier. This verifies the client's identity when exchanging the authorization code. The authorization server validates the authorization code and the code verifier and, if applicable, the client credentials. To validate the PKCE, the server uses the stored code challenge and code challenge method. By applying the code challenge method to the code verifier, the server can generate the same code challenge and confirm that the exchange is legitimate. If everything checks out, the authorization server responds with an access token and possibly a refresh token, depending on the server's configuration. Finally, the client uses the access token to request resources from the resource server on behalf of the resource owner. The resource server validates the access token and, if valid, returns the requested resources to the client, completing the process. Now let's see how the PKCE flow addresses the security challenge of the authorization code flow that we covered in the last lesson. Once again, we have the same malicious application, an interceptor that's capable of monitoring and intercepting browser or network traffic. This time, the user agent is, for example, a browser, and the client is a single-page application, configured as a public client in the authorization server. In the PKCE flow, the client has already generated a proof key for code exchange and securely stored the code verifier locally. The authorization server during the initial redirect request has stored the code challenge and the code challenge method. Now, when the authorization server redirects the resource owner back to the client via the user agent and provides an authorization code, the malicious application intercepts again because it's still monitoring the traffic. Then, the malicious application attempts to exchange the intercepted code by sending a post request for an access token. The authorization server will validate the authorization code, and the PKCE code verifier, I don't know, since the code verifier doesn't match the stored code challenge, the request will fail, resulting is an unauthorized response, leaving the hacker very sad. On the other hand, the legitimate client sends the correct post request with the authorization code and the valid code verifier, I know it. And there we go, the authorization server successfully validates the request and grants the client an access token. Now let's assume the malicious application tries to intercept the code verifier when the client sends it to the authorization server. That wouldn't work either, because the client sends the code verifier via a post request, which is typically encrypted with SSL TLS, once again leaving the hacker very sad. This additional layer of security, the requirement for the code verifier, prevents unauthorized access and solves the security challenge of the authorization code flow for public clients. Even though the PKCE flow was originally designed to address a security challenge for public clients, it is recommended for both public clients and confidential clients. PKCE was originally designed to protect the authorization code flow in mobile applications, but its ability to prevent authorization code injection makes it useful for every type of OAuth client, even web applications that use a client secret. With the code and the PKCE mechanism, this flow ensures security for both public clients and confidential clients, providing a critical layer of protection for public clients and enhancing security for confidential clients as well. Let's quickly recap the user-initiated to OAuth 2 flows we have covered so far, and walk through a decision tree to help you determine when to use each flow, ensuring your architectural decisions align with the right security needs. Implicit flow. The implicit flow is the simplest OAuth 2 flow and was originally designed for browser-based public clients. However, due to its inherent security risks, such as token transmission in the URL and its increasing obsolescence, this flow is generally discouraged unless there is a compelling reason to use it. Authorization code flow. The authorization code flow offers a more secure alternative to the implicit flow. It's specifically designed for confidential clients that can securely store sensitive credentials like the client secret. This makes it ideal for regular web applications that involve a backend server capable of securing these credentials. However, it's not suitable for applications that don't have this capability, such as single-page applications. PKCE flow, proof key for code exchange. The PKCE flow extends the security of the authorization code flow. It's designed to solve the security challenges, especially for public clients like single-page applications or mobile applications, but it can also be used and is recommended for confidential clients. This flow is a secure and practical choice not only for native mobile and desktop applications, but also for traditional web applications. Now let's move on to the decision tree, which wraps everything up and provides a step-by-step guide to making the right choice for user-initiated flows. We begin by evaluating whether the flow is user-initiated. If the answer is no, then the scenario is not applicable for user-initiated flows and we stop here. If yes, we proceed to the next crucial question. Now we determine if we are dealing with public clients or confidential clients. Can the client securely store client credentials? If yes, it's a confidential client and we proceed with the authorization code flow. The next step is to evaluate whether we can enhance security with PKCE. Is there a limitation to applying PKCE? See considerations. I'll cover those considerations in just a moment. If there are limitations, we stick with the authorization code flow and that is sufficient. If there are no limitations, we extend the flow with PKCE for confidential clients and we stop here. Now, let's see what happens if we are dealing with a public client. First, we check whether the client meets the following conditions. Is it browser-based application? Is there a solid reason not to use PKCE? See considerations. I will cover those considerations in just a moment. Is the risk of the implicit flow acceptable? If all conditions are met and the risks are acceptable, we proceed with the implicit flow for public clients. Otherwise, if any of these conditions are not met, we move forward with the PKCE flow for public clients. Here's what to consider when deciding whether PKCE is feasible for your use case. Prototypes or internal applications with time and budget constraints. In cases where you are developing a prototype for client demonstration or working on an internal application within a trusted environment, security enhancements like PKCE might not be the highest priority. Due to time or budget constraints, developers may opt for simpler flows if the system is not exposed to significant security risks. OAuth 2 authorization server constraints. If you are using an older OAuth 2 authorization server or custom-built solution, it may not support PKCE. In these cases, even if PKCE is recommended, the lack of support may force you to fall back on other alternatives. OAuth 2 client-side constraints. PKCE requires the client to generate and store a code verifier and code challenge, which might not be feasible for legacy systems or devices with limited capabilities. Other constraints: if you are working with external vendors or third-party applications where you don't have control over the client's configuration, PKCE might not be feasible. And for any other similar constraints where you don't have the option to implement PKCE due to the technical limitations or external dependencies, it's important to weigh the associated security risks carefully and consider the available alternatives. By carefully weighing these considerations, you can determine whether to prioritize PKCE for enhanced security or stick to alternative flows. In this chapter, we are going to explore several OAuth 2 extension flows that address the security challenges found in user-initiated flows. These extensions help to enhance security through different mechanisms and approaches. We'll begin by clearly defining the security challenges that these extensions aim to solve, using the same scenario from before, a hacker intercepting application traffic to exploit vulnerabilities. The first OAuth 2 extension flow we'll dive into is the JWT Secured Authorization Request, JAR. We'll explore how this flow works by walking through a step-by-step sequence diagram, discovering which client types it supports and how it mitigates security risks in OAuth 2 user-initiated flows. However, even with JAR, there may still be a security concern that could impact some project requirements. This is where JAR combined with JSON Web Encryption JWE comes into play, adding an additional layer of protection. To fully understand this, we'll first go over how asymmetric encryption works and how it differs from the asymmetric signing mechanism we covered earlier. Afterward, we will break down the JAR with JWE flow using a sequence diagram to see how it addresses the remaining security challenges. Even so, there may be specific challenges that need to be addressed for certain projects, which brings us to the final extension, the Pushed Authorization Request, PAR. We'll break down PAR step by step, starting with the core OAuth 2 roles, examining the client types it supports, the involved OAuth 2 endpoints, walking through the sequence diagram, and even the curl commands and required parameters. Finally, we will explore how to combine these approaches, such as using JAR with PAR or JAR with JWE and PAR, by summarizing the steps through a comprehensive sequence diagram. At the end of the chapter, we'll recap all the approaches we have learned. And as always, we'll conclude with a decision tree. We'll walk through it step by step, considering various requirements, environments, security levels, and project-specific factors, helping you ensure that your architectural decisions align with the right security measures for your use case. Up until now, everything looks perfect, right? But although we are quite satisfied with the security enhancement provided by the PKCE flow, there is still one challenge that applies to all user-initiated flows we have covered so far. Let's take a look back. Despite the security improvements, we still face a security challenge in the authorization request itself across all flows. But why? Let's uncover this together with the following scenario. We have the PKCE flow, where the user agent is a browser, and the client is a single-page application registered as a public client in the authorization server. The resource owner initiates the PKCE flow by attempting to log in. The client creates the PKCE proof key for code exchange and stores the code verifier securely as CVXY. The client then redirects the resource owner to the authorization server via the browser, including the coded challenge XY in the query parameters of the authorization request. But now, suppose the malicious application intercepts this request and manipulates the parameters, like replacing the coded challenge. The attacker creates a new PKCE, set code verifier CVAB, and replaces the coded challenge XY in the authorization request with their own. While technically difficult to pull off, this is not entirely impossible. The authorization server stores the attacker's manipulated code challenge AB and issues an authorization code. At the point where the authorization server redirects the resource owner back to the client, providing an authorization code, the malicious application intercepts this authorization code. The attacker sends a post request to exchange the authorization code for an access token, providing the code verifier that matches the manipulated code challenge CVAB. Now, the authorization server validates the request, and here we go, it works, providing the attacker with an access token, leaving the resource owner very sad. No integrity and authenticity are enforced when initiating the request, leaving room for tampering with sensitive parameters. And this is exactly the security challenge we face here. The potential to tamper with some query parameters of the authorization request. Not only the code challenge, but also other sensitive information like scopes and any other critical details. Although this attack is technically difficult, it still poses a risk across all user-initiated flows, including the implicit flow, authorization code flow, and even PKCE flow. Fortunately, there is an OAuth 2 extension flow designed specifically to address this risk, which we will explore in the next lesson. In this lesson, we are diving into the JWT Secured Authorization Request, or JAR for short. This extension to the OAuth 2 flows addresses the security challenge of the initial authorization request that we discussed in the last lesson. JAR is a security-enhancing extension that can be applied to all user-initiated flows that supports confidential clients, meaning it works with both the authorization code flow and the PKCE flow, but only with confidential clients. We'll explore why it is limited to confidential clients shortly. Let's take a look at how JAR works within the PKCE flow. We are still working with the same OAuth 2 roles. As usual, the resource owner initiates the flow by wanting to log in. The client first generates a PKCE proof key for code exchange and stores the code verifier securely. Next, the client creates the authorization request parameters that are typically sent as query parameters in the URL, such as client ID, redirect URI, scope, state, code challenge, and code challenge method. But instead of including these parameters in the URL, the client creates a JWT JSON Web Token and packages them into its payload. And then the client encodes the token, both the header and payload, in base64 URL format. The client then signs the JWT using its private key. The recommended signing algorithm here is asymmetric with RS256, RSA using SHA-256. Which ensures stronger security by utilizing a public and private key pair. This means that the client must securely store its private key for signing the JWT, as the integrity and authenticity of the token rely on this key. To validate the signature, the authorization server must also have access to the client's public key or know how to retrieve it. We have already covered the basics of asymmetric signing in the token validation lesson. And exactly because of the private key that should be securely stored by the client, we need to register the client as a confidential client. Once the JWT is signed, the client then sends the resource owner to the authorization server along with the signed JWT and client ID as query parameters. The authorization server validates the JWT's signature using the client public key and extracts the parameter from the token. From here, the server stores the code challenge and code challenge method, and everything proceeds as usual. The resource owner then authenticates, and the authorization server generates an authorization code and redirects the resource owner back to the client. Let's now see how the JAR flow addresses the security challenge we discussed in the last lesson, using the same scenario with a malicious application. The client begins by performing the 5 steps of the JAR flow. It first generates a PKCE with a code verifier of CVXY and creates the authorization request parameters such as the redirect URI, scope, and code challenge. In this case, the code challenge is equal to XY. Next, the client includes all these parameters in the JWT payload, then encodes and signs the JWT using its private key. After this, the client sends the JWT to the authorization server by redirecting the resource owner via the user agent. Now, suppose the malicious application intercepts this request again and attempts to manipulate the parameters like replacing the code challenge. The attacker generates a new PKCE with a code verifier of CVAB and it changes the code challenges from XY to AB in the token payload, sending the request to the authorization server. And here is where the critical difference lies. The first thing the authorization server does is validate the JWT signature using the client's public key. Since the attacker has modified the payload, the signature no longer matches the original signed authorization request. As a result, the authorization server detects the tampering and rejects the request, which makes the attacker very sad. Up until now, everything seems perfect, right? However, we still encounter a few issues. The first is the length of the token in the URL, which could present challenges in certain mobile applications. The second issue is a minor security concern, which might be critical in cases requiring a higher security level or strict compliance with regulations. Let's dive into the following scenario. Suppose the client needs to send sensitive information along with their direct authorization request, or due to compliance requirements, this information must be classified as confidential to comply with strict policies and regulations. For instance, we have an amount of 500 and the purpose of rent payment for a transfer transaction. The client includes this information in the JWTs payload and sends it to the authorization server. But once again, the malicious application intercepts and decodes it. While JR secures the integrity and authenticity of the authorization server, the JWT is still base 64 encoded in plain text, meaning any sensitive information in the JWT can be easily exposed if intercepted. Essentially, everything is in plain text, leaving sensitive information visible to the attacker, making the resource owner very sad. This reveals a key challenge: no confidentiality in the authorization request. And that's exactly the issue we will address together in the next lesson. Before we move on to the next lesson, let me briefly explain asymmetric encryption for ensuring confidentiality, because we'll need this concept in the upcoming lessons. It's actually very straightforward and similar to asymmetric signing for integrity and authenticity, which we covered in the first chapter. Let's return to our scenario with Bob and Alice. You might remember the evil guy who was trying to cause trouble by tampering with their messages. This time, Bob and Alice want to ensure not just the integrity of their communication, but also its confidentiality. So the evil guy cannot even read the messages. Here is how asymmetric encryption for confidentiality works. Instead of Bob having the private key and Alice the public key, like in signing, Bob gets the public key and Alice keeps the private key. The public key is openly shared while the private key is kept secret. When Bob writes a message, he encrypts it using Alice's public key. Since the public key is available to anyone, it ensures that only Alice, the holder of the private key, can decrypt it, keeping the message confidential. Once encrypted, Bob sends the message to Alice. She uses her private key to decrypt the message and read it. Since only Alice has the private key, we can be sure that no one else can read the message. To wrap up, asymmetric signing for integrity and authenticity. The private key signs data and the public key verifies the signature, ensuring that data has not been tampered with. Asymmetric encryption for confidentiality. The public key encrypts the message and the private key decrypts it, ensuring only the intended recipient can read it. Before we dive into JR with JWE, let's take a step back and understand what JWE JSON Web Encryption is all about. First, it's important to note that JWE is not an OAuth 2 extension flow on its own. Instead, it integrates seamlessly with JR JWT secured authorization request flow to enhance security by adding confidentiality to authorization requests. In simple terms, a JWT JSON Web Token can be signed using JWS JSON Web Signature to ensure the integrity and authenticity of the data. In cases where asymmetric signing is used, JWS also offers a non-repudiation. This means that the party who signs the token cannot later deny their involvement, because only the private key held by the original signer could have generated the signature, which can be verified with the public key. However, when confidentiality is required, meaning we want to protect sensitive information within the token from unauthorized access, JWE JSON Web Encryption comes into play. When it comes to OAuth 2, the JR extension ensures the integrity and authenticity of the authorization request parameters through the use of assigned JWT. JWS. But in some cases, we also need to guarantee the confidentiality of the authorization request. This is where the combination of JR with JWE proves useful. In simple terms, JR with JWE works similarly to JAR, but with an added step. It encrypts the token. First, as usual, the resource owner initiates the flow. The client then performs the same steps as JAR, generates a PKCE and stores the code verifier securely, creates the authorization request parameters, including some sensitive information like an amount of 500 and the purpose rent payment that needs to remain confidential. then packages these parameters into a JWT, encodes and signs the token to ensure integrity and authenticity. Here is the key distinction from JAR. In JWE, the client also encrypts the token before sending it to the authorization server. We have covered the encryption mechanism in the asymmetric encryption lesson. For security reasons, we don't use the same key pair for encryption that was used for signing. Instead, we use a new key pair, one public key for the client to encrypt the token and one private key for authorization server to decrypt it. The client signs the token with its private key and encrypts it with the authorization server's public key. The authorization server verifies the signature with the client's public key and decrypts the token with its private key. Now let's see how this extension solves the security challenge from the JAR scenario. At the same point where the client redirects the resource owner to the authorization server, the attacker intercepts the token again and attempts to decode it and access the sensitive information. But it doesn't work. The token is encrypted and only the authorization server holds the private key to decrypt it, leaving the attacker very sad once again. Up until now, everything seems perfect, but we still face some challenges despite the security improvements. The first challenge comes after signing, encrypting, and packaging the token with the authorization parameters. Let's take a look at how long the URI has become. We have encountered this challenge before with the JAR extension as well. This approach can lead to issues such as increased URI length, which is problematic for mobile applications. And there is also the potential security risk if the URI is locked or intercepted. Even with signing or encryption, URI might be recorded in logs or caches, exposing sensitive information unintentionally. Moreover, let's discuss how difficult it is to manage the keys, renewing, revoking, and so on, especially as the architecture and the number of clients grow. Fortunately, there is another extension that addresses these challenges while continuing to secure the authorization parameters. We'll dive into that in the next lesson. In this lesson, we'll explore the pushed authorization request BAR. BAR is the second OAuth 2 extension flow designed to enhance the security of authorization request parameters, following JAR JWT secured authorization request. However, unlike JAR, which focuses on securing the authorization request through JWT signatures and encryption, BAR takes a different approach by addressing the security concerns related to the redirection of authorization requests. Instead of sending sensitive authorization parameters in the redirect request, BAR improves security by sending these parameters directly to the authorization server via a secure POST request. Ideally, this communication is encrypted using SSL TLS. The authorization server stores the parameters and returns a reference or request URI back to the client. The client then redirects the resource owner to the authorization server using this reference in the query parameters. Let's dive in and see exactly how BAR works through a sequence diagram applied to the PKCE flow. Unlike JAR, which is only applicable to confidential clients, this extension BAR can be used by both public clients and confidential clients. As usual, the flow starts with the resource owner initiating the process. The client then creates a PKCE, generating and storing the code verifier locally. Now, here is where the key difference from JAR comes into play. In the BAR flow, the client doesn't sign and encrypt the authorization request parameters and then redirect the resource owner via the user agent. Instead, the client sends these parameters directly to the authorization server via a POST request. For that, it creates these parameters as a POST request payload. Here is how the curl request might look. It's a POST request, pointing to the BAR endpoint provided by the authorization server. The client authenticates itself in the request header using HTTP basic authentication, where it includes the client ID and client secret. In the POST request payload URL encoded, the client provides all necessary authorization request parameters, such as scope, redirect URI, code challenge, and other related data. The client then sends the POST request to the authorization server. The authorization server authenticates the client, if confidential. It validates the authorization request parameters. The server then generates a request URI, which is a short-lived reference to the authorization request. It stores the parameters and returns the request URI back to the client. Here is an example of how the response looks. Now, the client proceeds with the redirect request, but this time it doesn't include all the authorization request parameters in the query. Instead, it includes only the request URI as query parameter. The authorization server then validates the request URI. If valid, it fetches the associated authorization request parameters and processes the request as usual. This includes authenticating the client, confirming scopes, and so on. PAR improves security by mitigating risks related to URL-based redirection, but it doesn't inherently cover aspects like integrity, authenticity, non-repudiation, or confidentiality by default. However, if your security requirements demand these features, combining PAR with JAR can be a useful approach. Now that we have explored various OAuth 2 extension flows for securing authorization request parameters, we also have the option to combine these extensions for even stronger security. For example, we can use the PKCE flow with JAR combined with PAR to ensure integrity, authenticity, and non-repudiation, along with all benefits of PAR that we discussed in the last lesson. Alternatively, we can combine JAR with JWE and PAR to add an additional layer of confidentiality. Let's walk through an example of how this might work using the following sequence diagram. As usual, the resource owner initiates the flow. The client then performs a series of actions. It generates the PKCE and securely stores the code verifier. The client creates the authorization request parameters, then packages these parameters into a JWT payload, encodes and signs the token using its private key, ensuring integrity, authenticity, and non-repudiation. Next, the client encrypts the token using the authorization server's public key to ensure confidentiality. Finally, the client places the resulting JWT in the body of a POST request and sends it to the authorization server. The authorization server authenticates the client if confidential. It decrypts the JWE using its private key. It validates the JWS signature using the client's public key. Then it validates the authorization request parameters. It generates a request URI and stores the authorization request parameters. Finally, the authorization server returns the request URI to the client. From here, the flow proceeds as usual for PAR. The client redirects the resource owner to the authorization server, providing the client ID and the request URI as query parameters, and the rest of the process continues as we have covered before. Now that we have a comprehensive understanding of how these OAuth 2 extensions can be combined to enhance the security of user-initiated flows, you might be wondering, do we really need all these extensions in every scenario? When should we use JAR? JAR with JWE, PAR, or even a combination of them? In the next lesson, we'll recap all the OAuth 2 extensions we have covered so far and explore when to use each one based on different project requirements and security needs. Now let's recap the OAuth 2 extensions we have covered to enhance the security of authorization request parameters. First, we have the JWT Secured Authorization Request, JAR. This extension ensures the integrity, authenticity, and non-repudiation of authorization requests, addressing gaps in standard user-initiated flows. JAR works by signing authorization request parameters using a JWT, which not only prevents tampering but also provides verifiable proof that the request originated from the legitimate client, ensuring its authenticity and non-repudiation. Next, we discussed JAR with JSON Web Encryption, JWE. While JAR alone focuses on signing, JWE addresses the potential information exposure risk present in JAR by encrypting the JWT. This adds a layer of encryption, ensuring that sensitive information within the authorization request is protected from being exposed during transmission. Finally, we explored pushed authorization request PAR. PAR solved practical problems such as URL length limitations and security concerns associated with long URLs that could be locked or intercepted. It simplifies the process by allowing clients to push authorization request parameters directly to the authorization server via a POST request. The server then issues a reference request URI that the client uses in the authorization request. Also, it is important to note that you have the possibility to combine extensions together to further enhance security and meet various security requirements and levels. For example, you can combine PAR with JAR and JWE. This allows you to use PAR for practical advantages like pushing authorization requests via POST, while also ensuring integrity, authenticity, non-repudiation, and confidentiality through JAR and JWE. Now, let's talk about when to use each OAuth 2 extension. As always, it depends, but I am going to walk you through some key points that will help you make solid architectural decisions. We will go step by step through a decision tree that helps determine which OAuth 2 extension flow is best suited for your use case or project situation. Let's start by asking the first essential question. Is there a need to enhance security? If the answer is no, perhaps it's a prototype, an internal application within a trusted environment, or handling non-sensitive data, then extra security may be unnecessary and we can stop here. If the answer is yes, we continue forward to the next step. Next, we check if the authorization server supports PAR, Pushed Authorization Request. If the authorization server doesn't support PAR, we proceed to the next OAuth 2 extension, JAR, JWT Secured Authorization Request. We'll cover the JAR path shortly. If the authorization server supports PAR, we can use it as our first security layer, which mitigates the risks related to URL-based redirection. Then we move forward to the next step. We then check whether the authorization server supports PAR with JAR, and more importantly, if all the key JAR conditions are met. I'll go over these key conditions and considerations shortly. If JAR isn't supported or the conditions are not fully satisfied, we end here with just PAR. If JAR is supported and all key conditions and considerations are met, we can use PAR with JAR as our second security layer, which adds integrity, authenticity, and non-repudiation to the flow, while also mitigating URL links and redirection risks. Now we move on to the final layer of security by checking whether the authorization server supports PAR with JAR combined with JWE, JSON Web Encryption. If confidentiality or strict compliance requirements are not critical, we stop here. If confidentiality is important and supported, we proceed to use PAR with JAR and JWE as the third security layer, which adds confidentiality to protect sensitive information in the authorization request. Keep in mind that there is already a confidentiality layer in place through SSL TLS encryption with PAR. However, if you need an additional more specific confidentiality layer tailored to your use case, you might want to consider using JWE. Now let's go back to the JAR path in case PAR is not supported by the authorization server. First, we ask if the authorization server supports JAR and whether the URI links is not an issue and all JAR key conditions and considerations are met. I'll go over these key conditions and considerations shortly. If JAR is not supported or any of these conditions are not met, the flow ends here. If everything checks out, we proceed with JAR as our first security layer, which ensures integrity, authenticity, and non-repudiation. Finally, we check if the authorization server supports JAR combined with JWE, asking whether confidentiality or strict compliance requirements are critical. If confidentiality is not a concern, we stop here. If confidentiality is crucial, we can use JAR with JWE as the second security layer, adding encryption to protect sensitive data in the authorization request. Now that we have worked through a decision tree, let's move on to the key conditions that must be met in order to use JAR. First off, the client has to be a confidential client. This is crucial because the client needs to be able to securely manage and store private key to sign the JWT. Next, budget and resources are important. The organization should have the necessary infrastructure and resources to handle the complexity of JAR, especially when it comes to managing keys like PKI, public key infrastructure. If you already have a solid PKI setup, this could be a great fit. And finally, you should really ask yourself, do you need the benefits of JAR in your specific case? Things like integrity, authenticity, and non-repudiation are great, but if your use case doesn't require them, you might be adding too much complexity for little return. Now, in addition to these conditions, there are a couple of important considerations I highly recommend thinking about. First, weigh security versus performance. Using JAR, or even more so, JAR with JWE, can impact performance, especially in high traffic systems or performance sensitive applications. Those cryptographic operations take time and can introduce latency. And of course, there is a matter of complexity. Does your infrastructure have the capability to manage the added complexity? Things like security scalability. Can your system handle key rotation and management for multiple clients at scale? Lastly, if you are using JWE, debugging can get tricky. Encrypted tokens make troubleshooting harder, so you will need to make sure you have good observability and monitoring tools in place to catch any issues that come up. And that wraps our guide for determining which OAuth 2 security extension flow to use. This decision-making process offers a structured orientation, helping you navigate the key conditions and considerations involved. By carefully weighing these factors, you can ensure that you are applying the most suitable security layers for your project's specific needs and compliance requirements. In this lesson, we are going to talk about a special OAuth 2 flow, the resource owner password credentials flow. If you recall from our earlier lessons, we have emphasized the importance of not sharing user passwords directly with clients. This was one of the core reasons for the creation of OAuth 2, starting with some snippets as a story and hesitating application Magic Snap, and continuing through our demo with OneDrive and Photobee across all OAuth 2 user-initiated flows, Implicit, Authorization Code, and PKCE. We explored the critical importance of redirecting users to the authorization server. However, there are some rare and special cases where redirecting the user may not be possible, and the client must handle the credentials directly. In my own experience, I have encountered a few situations in projects where this happened, and these can be broken down into three main categories. Technical constraints. In certain environments, technical limitations might make redirection impossible, meaning the client has to manage credentials directly. Client API limitations. There are times when the organization doesn't have control over the client's provided APIs, making it difficult or impossible to implement redirection in the flow. Compliance or legacy system constraints. In some cases, compliance regulations or legacy system limitations don't allow redirection, so an alternative method is needed. In such scenarios, while it's not recommended, you might still want to use OAuth 2. So the question becomes, does the client always need to redirect the resource owner to use OAuth 2? This is where the resource owner password credentials flow comes into play. Let's explore how this flow works. First, as always, we begin with the OAuth 2 roles involved. This flow works with public and confidential clients, though it's highly recommended to be used only with confidential clients due to security concerns. In this flow, only the token endpoint is involved. There is no interaction with the authorization endpoint, as redirection is not part of the process. The user initiates the flow by entering their credentials directly into the client. The client then sends a POST request to the token endpoint to obtain an OAuth 2 access token. Here's a look at the typical curl command for this flow. In the request body, the client provides grant type equals password, indicating the resource owner password credentials flow is being used, the username and password of the resource owner, the client ID and the client secret, optionally OAuth 2 scopes. Note that the client secret is only required for confidential clients, which is highly recommended for added security. Afterward, the authorization server verifies the resource owner's credentials, validates the client's credentials, if confidential. If everything checks out, it generates and returns an OAuth 2 access token and possibly a refresh token. From here, the process is like other flows. The client uses the access token to access the resource owner's resources from the resource server. The resource server validates the token and provides the requested resources. However, while this flow works, it is officially deprecated in OAuth 2.1 due to the security risks it presents. Many identity and access management components still support this flow because of specific legacy cases, but it's crucial to be aware of the risks involved. Here are some risks associated with this flow and the reasons for its deprecation. First, it exposes user credentials to client applications, increasing the risk of theft if the client is compromised. It also violates the OAuth 2 principle of keeping credentials confidential. Additionally, there is no delegation, meaning the client gets full access, matching the user's permissions. Finally, this flow doesn't support modern security practices, like multi-factor authentication or advanced authentication, leading to non-compliance with current standards. To wrap up, avoid using this flow whenever possible. Avoid it as long as you can, and never fully trust the client, even if it is your own application. If there is no other option and you trust the client completely, ensure you implement it carefully and securely. Now that we have covered all the OAuth 2 user-initiated flows, let's dive into the machine-to-machine flows. Here we only have the client credentials flow. In these scenarios, there is no resource owner, so our OAuth 2 roles are reduced to just three: the client, the authorization server, and the resource server. The client must be a confidential client, as it represents a server-side application running on the developer's network. In this flow, we will use the token endpoint to request tokens, but we will not use the authorization endpoint as it's only relevant for user-initiated flows. In this flow, the client initiates the process by sending POST request with its credentials to retrieve an access token. Here is how the curl command looks. The client sends a post request to the token endpoint. Content type is set to URL encoded from data. The grant type is set to client credentials, indicating the use of this flow. Client credentials such as client ID and client secret are provided for authentication. Optionally, scopes can be included for fine-grained access. The authorization server verifies the client's credentials, and if everything checks out, it sends back an access token. The client uses this access token to access resources on the resource server, not on behalf of a user but on behalf of itself. This is an important distinction and brings us to the possible use cases for this flow. The resource server validates the access token and, if valid, provides the requested resources to the client, completing the flow. Before exploring the use cases for this flow, it's important to remember that it's designed for actions carried out independently of any user context. It's not designed for actions involving user representation or device-specific authentication. Those situations will be addressed in later flows. Now let's explore where this flow is most applicable, starting with external service integration. In some scenarios, you may need your application to integrate with external or third-party services. This might include partners accessing your APIs to exchange data or add functionalities, or your application fetching external data like weather updates to display in a user dashboard. Moving on, another common scenario for this flow is internal server-to-server communication. Sometimes internal services need to communicate directly to support backend operations and data sharing within the organization. For instance, a backend service might use an internal API to update exchange rates, or a reporting tool might pull data from multiple internal services to generate insights. Another use case is automated system tasks, which includes scheduled jobs and maintenance scripts that run independently of user actions. These could be scheduled jobs like cron jobs for data syncing or backups, scripts that handle data migration or cleanup, or monitoring tools that check service health and performance via API access. Keep in mind that just because a user isn't initiating the flow doesn't automatically make this flow the right choice. The critical factor is that the action should not require user delegation or context. It must be purely service-based, with the client acting independently of any user. If backend services need to perform actions on behalf of a user or with a user context, we'll cover specific flows for that in later lessons. Now let's quickly recap everything by walking through a decision tree that helps determine if the client credentials flow is the right choice for your use case. We start with the first essential question. Does the current action need user involvement? If the answer is yes, meaning the action requires direct user interaction or consent, then user-initiated flows are the right choice, and we stop here. If the answer is no, we move on to the next question. Is the client a device with limited input capabilities? This is where the device code flow comes in, which is particularly useful for devices like IoT gadgets or smart TVs that need user authorization but have limited input options. We'll cover the device code flow in detail in a later lesson. If the answer is no, we continue to the next question. Does the client need to perform this action on behalf of a specific user, requiring user delegation? If so, we use the token exchange flow, as it allows a machine to perform actions within a user's context. We'll dive deeper into the token exchange flow in a later lesson as well. Finally, if none of these conditions apply, meaning the action is performed purely on behalf of the client without any user context, then the client credentials flow is the right choice. In this lesson, we'll discuss the device code flow. This flow is user-initiated, but it is unique compared to the traditional flows we have learned before. It's designed for situations where authorization is needed, but certain constraints exist, such as with devices like smart TVs or printers. These devices often lack the ability to accept user credentials directly. This is where the device code flow comes into play. Let's dive in and see how it works. As always, we start with the OAuth 2 rules. In this flow, an additional component is a secondary device, which acts as a user agent for the resource owner. This device should be able to open the login interface of the authorization server, such as a smartphone or a computer. The client is a device capable of sending outbound HTTP requests, like a smart TV or a printer, but it cannot receive incoming requests. Since the client operates in the user's network and cannot secure secrets, it must be configured as a public client. The resource owner initiates the process, for example, by pressing a button or starting the device. The client sends an authentication request to the authorization server. Here's how the card command looks. The client sends a post request to the device authorization endpoint of the authorization server. The content type is set to URL encoded from data. It includes a client ID to identify the client and optionally specifies scopes. The authorization server generates a verification code and a verification URI. Optionally, it may also provide the URI as a QR code, enabling users to scan it using their smartphones. The authorization server responds with several key pieces of information. It provides a device code that the client uses to poll for the user's authorization status. A user code is also provided, which is a short, easy to enter code for the user. Additionally, a verification URI is shared, which the user must open on an external device. Sometimes, the server also provides a verification URI complete, which includes the user code pre-filled to make the process easier. Expires in specifies how long the codes are valid, and the interval how long the client should wait before polling again. The client displays the verification URI and the user code to the user. Here's the example process from Netflix. The user opens the verification URI on a secondary device, either manually or by scanning a QR code if available. Once the verification page is open, the user enters the device code displayed on the client. The user then logs in to the authorization server or creates a new account depending on the situation. The user may also review and approve the requested scopes during this step. At this stage, the authorization server validates the device code and user credentials. If everything checks out, it links the authorization to the device code, meaning the authorization server associates the user's consent and authentication with the specific device code provided to the client earlier in the flow. Meanwhile, the client begins polling the token endpoint at the specific interval, asking the authorization server for the authentication status. Here's how the curl command looks. The client sends a post request to the token endpoint of the authorization server. The content type is set to URL encoded from data. It includes a client ID to identify the client, and the device code issued earlier to link the request to the specific device. The grant type is set to device code to indicate the use of the device code flow. The authorization server responds in one of three ways. It may return an access token if the user has successfully authenticated and consented. It may indicate that authorization is still pending if the user hasn't completed the process, or it may deny access if the user rejects the request or the code expires. Once the client receives a valid access token, it can use it to interact with the resource server on behalf of the resource owner. For example, in Netflix, the client can use the access token to stream movies included in the user's subscription. And that's how the device code flow works. It provides a secure and user-friendly way to handle authorization on devices with limited input capabilities. Up until now, we have explored various OAuth 2.0 initiate flows. These include the authorization code flow where the user is redirected to the authorization server for authentication. We have also discussed machine-to-machine client credentials flow where the client itself authenticates with the authorization server, and the resource owner password credentials flow where the user directly authenticates with the client. But what if authentication has already taken place elsewhere, with another trusted system known as an identity provider? This is common in a federated identity setup where one system manages authentication that other trusted systems rely on. In such cases, does the user or client need to go through the authentication process again to obtain an OAuth 2 access token? The answer is not necessarily. If the authorization server trusts the identity provider and the client can provide a valid JWT or SAML assertion that proves authentication has already taken place, an OAuth 2 access token can be issued without re-authentication. This is where assertion flows come into play. These flows allow a client to use an existing authentication session to securely and seamlessly obtain OAuth 2 access tokens, integrating identity providers into an OAuth 2 ecosystem with minimal friction. There are two main assertion flows in OAuth 2. The JWT bearer assertion flow and the SAML2 bearer assertion flow. These flows can be used in the context of OAuth 2 both as a grant type and as a client authentication method in other OAuth 2 flows, which we will explore in a later lesson. In this lesson, we will focus on these assertion flows as an OAuth 2 grant type. If you recall from previous lessons, grant type refers to the method by which an application obtains an access token. In simple terms, the JWT bearer assertion flow allows a client to obtain an access token by presenting a previously issued trusted JWT that asserts the user's or client's identity, eliminating the need for re-authentication. The SAML2 bearer assertion flow works similarly, but instead of a JWT, it uses a SAML assertion. The key point here is that the identity provider must be trusted by the OAuth 2 authorization server. Now let's dive into the JWT bearer assertion flow. As always, we start with the OAuth 2 rules. In this scenario, the client can be either public or confidential client. This flow utilizes the OAuth 2 token endpoint. A new component to consider in this flow is the external trusted identity provider, which the authorization server relies on. This is why establishing a trust relationship between the identity provider and the authorization server is essential. The identity provider can be an OpenID Connect compliant provider or any identity provider capable of issuing JWTs. The resource owner initiates the flow by logging into the identity provider and providing their credentials, such as a username and password. Once authenticated, the identity provider issues a JWT token, referred to as a JWT bearer assertion in this context, and returns it to the service provider, which acts as the OAuth 2 client. The client receives the JWT bearer assertion and sends a POST request to the token endpoint of the authorization server to exchange the assertion for an OAuth 2 access token. Here is how the curl command looks. The client sends a POST request to the token endpoint. The content type is set to URL encoded form data. The grant type is set to JWT bearer, indicating the use of the JWT bearer assertion flow. The assertion parameter contains the JWT bearer assertion to be exchanged. Optionally, the request can include a scope parameter for fine-grained access control. If the client is confidential, credentials such as client ID and client secret are included in the request. Next, the OAuth 2 authorization server validates the JWT bearer assertion, mapping any claims within it, such as user attributes or roles. If everything checks out, the authorization server generates an OAuth 2 access token and returns it to the client. This token allows the client to act on behalf of the resource owner who initiated the request with the identity provider. If the request was machine initiated, the access token represents the machine's identity. From this point onward, the process is similar to other OAuth 2 flows. The client uses the access token to perform actions or request resources from the resource server. The resource server in turn validates the access token and if valid, returns the requested resources, completing the process. Now let's move on and see how the SAML bearer assertion flow works. This flow is very similar to the JWT bearer assertion flow, but instead of a JWT, the identity provider generates a SAML2 assertion. This means the identity provider is a SAML identity provider. If you are unfamiliar with SAML, it's an older authentication protocol similar to OpenID Connect that generates assertions in XML format. In SAML terminology, the OAuth 2 client is referred to as the service provider, and the resource owner is called the principal. The client receives the SAML bearer assertion and sends a POST request to the token endpoint of the authorization server to exchange the assertion for an OAuth 2 access token. Here's how the curl command looks. The client sends a POST request to the token endpoint. The content type is set to URL encoded form data. The grant type is set to SAML2 bearer, indicating the use of the SAML bearer assertion flow. The assertion parameter contains the SAML bearer assertion to be exchanged. Optionally, the request can include a scope parameter for fine-grained access control. If the client is confidential, credentials such as client ID and client secret are also included in the request. Next, the OAuth 2 authorization server validates the SAML bearer assertion, mapping any claims within it, such as user attributes or roles. If everything checks out, the authorization server generates an OAuth 2 access token and returns it to the client. This token allows the client to act on behalf of the resource owner who initiated the request with the identity provider. If the request was machine initiated, the access token represents the machine's identity. From this point onward, the process is similar to other OAuth 2 flows. The client uses the access token to perform actions or request resources from the resource server. The resource server in turn validates the access token and if valid, returns the requested resources, completing the process. Now let's discuss when to use JWT and SAML assertion flows. If all the following conditions are met, JWT or SAML assertion flows are suitable for integration with a new OAuth 2 environment. First, OAuth 2 authorization server support. The authorization server must support the intended assertion flow. Not all OAuth 2 authorization servers do, so it's essential to verify this before proceeding. Second, existing identity provider that authenticates users. You should already have an identity provider in place that handles user authentication independently of your OAuth 2 authorization server. Third, trust relationship between identity provider and OAuth 2 authorization server. It's crucial to establish a trust relationship, ensuring that your authorization server can rely on the identity provider. For example, if both are part of your system infrastructure or organization. Fourth, identity provider issues JWT or SAML assertions. The identity provider must be capable of issuing JWT or SAML assertions for user or client authentication, including the necessary claims and signatures aligned with OAuth 2 assertion flow requirements. Lastly, need for integration with OAuth 2 security domain. If the first four conditions are met, and you have a requirement or use case that drives the need for integration with an OAuth 2 environment based on existing authentication with our authentication, then OAuth 2 assertion flows should be considered. Based on my experience working with various integrations, let's move on to some use cases for OAuth 2 assertion flows using JWT and SAML. The assertion flows provide solutions for integrating various systems seamlessly, so it is essential to understand when and why to use them. First, we have trusted external partners integration. The purpose here is to allow external partner users to access your OAuth 2 protected resources. In this scenario, the partner's identity provider is responsible for handling user authentication. This ensures that external partners can use their own authentication systems while still being granted access to resources within your security domain. Next is internal security domain integration, specifically for compliance-driven segmentation. The main goal is to integrate internal domains with the same organization that adhere to different compliance standards. For instance, one domain might follow GDPR requirements, while another may be subject to HIPAA regulations. Assertion flows enable users to access resources across these domains without compromising compliance policies. We also have internal security domain integration in the context of bridging legacy and new systems. This use case comes into play when legacy systems use SAML while newer systems operate on OAuth 2. The objective is to enable these systems to work together seamlessly. The assertion flow allows for the integration of legacy SAML-based authentication with modern OAuth 2-based systems without major overhauls. Another significant use case is migration scenarios. During phased migration that could span months or even years, both old and new systems must operate side by side. Using JWT or SAML assertion flows allows for a seamless transition where users authenticated by a legacy identity provider can still access OAuth 2 resources. This approach ensures that service interruptions are minimized, providing a smooth user experience during the migration process. Integrating existing SAML systems with OAuth 2 is another practical use case. Here, the aim is to enable existing SAML-based single sign-on systems to access OAuth 2 protected APIs. By using assertion flows, you can avoid significant changes to the established infrastructure while achieving the necessary integration. Lastly, we have multi-organizational collaboration platforms. These platforms often serve users from multiple organizations, each with its own identity provider. The assertion flow supports collaboration across these organizations by allowing the platform's authorization server to accept assertions from various trusted identity providers. This enables seamless cross-organizational access and interaction. Now, if you remember from previous lessons, we used the client ID and the client secret to authenticate confidential clients with the authorization server. This was consistent across all flows that used confidential clients. In user-initiated flows like PKCE and Authorization Code flow, the client authenticates itself with the client secret. Even in the client credentials flow, the client used the client secret for authentication. In fact, the client secret is just like an application password that the client uses for authentication. In some cases, we may need stronger authentication methods, perhaps due to various security levels or stricter security requirements. So the question arises, are there other client authentication methods in OAuth 2 besides the client secret? We have at least 4 client authentication methods in the context for OAuth 2. Authentication with the client secret, JWT bearer assertion, SAML bearer assertion, and X509 certificate. If you remember from the lesson on bearer assertion flows, the JWT bearer assertion and the SAML bearer assertion can be used both as grant type and as a client authentication method. We already covered these as grant type, and here we will explore them again, but now as client authentication methods. In simple terms, the client secret is a basic and standard method where the client uses a predefined secret, like an application password, to authenticate itself. In the JWT bearer assertion, the client authenticates itself by generating and signing a JWT locally, either symmetrically or asymmetrically. In the SAML bearer assertion, the client authenticates itself using a SAML assertion, which can be obtained either locally or from a SAML identity provider, and then uses the assertion to authenticate with the authorization server. In the X509 certificate method, the client uses a client certificate similar to server certificates for websites to authenticate itself. Before we dive into the client authentication methods, I want to note that these client authentication methods are applicable to all OAuth 2 confidential clients. Whether in user-initiated flows, machine-to-machine flows, the resource owner password to credentials flow, and so on. The key point here is not the flow but the authentication of the confidential client. For simplicity, I will explain them using the client credentials flow without focusing on the resource owner aspect. But in principle, they work the same way in user-initiated flows. However, the resource owner part isn't relevant for this particular context. Now, let's start with the client secret authentication method, the simplest one and the one we have seen in all other flows that involve confidential clients. As always, we start with the OAuth 2 roles, focusing on the machine-to-machine client credentials flow. In this flow, the client has a client ID and a predefined client secret, which is securely stored, essentially serving as an application password. The client initiates a POST request to the token endpoint to obtain an OAuth 2 access token, using the client secret to authenticate itself. The authorization server verifies the client ID and the client secret. If everything checks out, the server issues an OAuth 2 access token and returns it to the client. In the authorization code flow, the process is similar. The client secret is included in the request body for client authentication, as we previously discussed. Now, let's explore how the client credentials flow functions when using the JWT bearer assertion client authentication method. Remember that this method can involve either symmetric or asymmetric signing. Symmetric signing relies on a single shared secret key for both signing and verification. It's simple and fast, but carries greater risk if the shared secret is compromised. Asymmetric signing uses two keys, a private key for signing and a public key for verification, offering higher security and enabling public verification without exposing the signing key. Let's start with the JWT bearer assertion using symmetric signing. Again here, we have Bob and Alice, who both securely stored the shared secret. Bob represents the OAuth 2 client and Alice is the OAuth 2 authorization server. Additionally, we include the resource server to cover all the OAuth 2 roles for the machine-to-machine client credentials flow. Here is how the flow works. The client creates a JWT token and signs it using the shared secret. The client sends a POST request to the token endpoint, including the signed JWT bearer assertion as the client's authentication. The curl command is similar to the one used in the standard client credentials flow, but instead of the client secret, the signed JWT is included in the client assertion parameter. An additional parameter, client assertion type, is included to indicate the use of the JWT bearer assertion method. The authorization server verifies the token using the shared secret. If everything checks out, it issues an OAuth 2 access token and returns it to the client. Now, let's move on to the JWT bearer assertion with asymmetric signing. Again here, we have Bob and Alice. Bob holds and secures a private key, while Alice holds the corresponding public key. Bob represents the OAuth 2 client, and Alice is the OAuth 2 authorization server. Also the resource server to complete the OAuth 2 roles for this flow. The client creates a JWT token and signs it with a secured private key. The client sends a POST request to the token endpoint, including the signed JWT bearer assertion for authentication. The curl command structure remains the same as with symmetric signing. The authorization server verifies the token using the public key. Alternatively, the client can make the public key accessible via an API, similar to how tokens are validated by retrieving the public key from the authorization server. If everything is valid, it issues an OAuth 2 access token and returns it to the client. An alternative, less common approach is for the client to obtain the JWT from an identity provider that generates JWT assertions instead of creating it locally. In this case, the client retrieves the JWT assertion from the identity provider and uses it for authentication with the authorization server. This setup requires a trust relationship between the identity provider and the authorization server, along with specific configurations such as registering the identity provider's public key with the authorization server for signature verification. While this method is less frequently used, it can be advantageous in specific project scenarios. In the authorization code flow, the process is similar. However, instead of including the client secret in the request body, the JWT assertion is included along with the client assertion type parameter to indicate the use of the JWT bearer assertion as the client authentication method. Now let's take a look at how client authentication using a SAML bearer assertion works. As always, we start with the OAuth 2 roles. In this lesson, I will not go into the detail of SAML or the creation and verification of SAML assertions to keep the focus on OAuth 2. In general terms, the client creates a SAML assertion in XML format and signs it with a secured private key. The client then sends a POST request to the token endpoint, including the signed SAML bearer assertion for authentication. Establishing a trust relationship between the client and the authorization server is essential, which involves specific configurations such as registering SAML metadata and providing certificates to the authorization server. The curl command for this process is similar to the one used in the standard client credentials flow, but instead of including the client secret, the base64 encoded signed SAML assertion is provided in the client assertion parameter. An additional client assertion type parameter is used to specify the SAML bearer assertion method. The authorization server verifies the SAML assertion. If everything is valid, it issues an access token and returns it to the client. Alternatively, the client can obtain the SAML assertion from a SAML identity provider instead of generating it locally. In this case, the client retrieves the SAML assertion from the identity provider and uses it for authentication with the authorization server. This approach requires a trust relationship between the identity provider and authorization server and includes configurations such as registering SAML metadata and exchanging certificates for signature verification. For the authorization code flow, the curl command for using a SAML bearer assertion as a client authentication method is similar to the standard authorization code flow command. But instead of including the client secret, the encoded SAML assertion is provided, with the client assertion type parameter set to indicate the use of the SAML bearer assertion method. Before we delve into X509 certificates, it's important to note that mutual TLS, or MTLS for short, with X509 certificates is used in OAuth 2 not just as a client authentication method, but also as an advanced security mechanism for securing access tokens. We'll explore this aspect in a later lesson. Now let's examine how client authentication works using an X509 certificate. Client authentication with an X509 certificate is more complex than other methods, but it provides one of the highest level of security for client authentication in OAuth 2. This method is based on mutual authentication. The client authenticates itself by presenting an X509 certificate, and the authorization server also presents an X509 certificate to authenticate itself. MTLS is a secure protocol that builds upon standard TLS, which was previously known as SSL. The concept is similar to server certificate authentication, but extends it to include the client, ensuring a secure exchange when obtaining an OAuth 2 access token. This approach requires a robust public key infrastructure, PKI, to manage certificates. Alternatively, self-signed certificates can be used for smaller or internal systems, but they lack the inherent trust provided by a PKI. I will not dive deeply into PKI as I want to keep the focus on OAuth 2. However, we do need to cover some essential concepts to better understand this approach. First, we are going to understand what an X509 certificate is, what a certificate authority is, and how the chain of trust and verification work. Let's start with the X509 certificate. An X509 certificate is a digital certificate that binds a public key to an entity, such as a server, client, or individual, and is used to verify identity and secure communication. These certificates are issued by a trusted certificate authority, CA for short, and are widely used for securing communications over the internet. They contain key pieces of information including the subject, issuer, validity period, public key, and signature, among other extensions. The subject identifies the entity, like a client or server that the certificate is issued to. The issuer refers to the certificate authority or CA that issued the certificate. The validity period specifies the time frame during which the certificate is valid and can be trusted. The public key is used for cryptographic operations such as verifying signatures. And lastly, the signature is a digital signature created by the certificate authority. This signature ensures the certificate's authenticity, confirming it was issued by a trusted certificate authority, and its integrity, meaning it hasn't been modified since its issuance. Just like server certificates used in TLS SSL to secure server communications, X509 certificates can also be used for server and client authentication, like mutual TLS in OAuth 2, email encryption and signing, code signing, and other secure communications. These certificates play a crucial role in MTLS, where both parties in a connection, client and server, verify each other's identity through their respective certificates, providing a high level of security during client authentication and OAuth 2 flows. We have mentioned that these certificates are signed by a trusted certificate authority. But what exactly is a certificate authority? A certificate authority is a trusted organization responsible for issuing, signing, and managing digital X509 certificates. This organization can be an external third party such as trusted certificates authorities like DigiCert, Global Sign, and Let's Encrypt, or an internal certificate authority used within an organization that already has a public key infrastructure in place. The certificate authority operates by creating an X509 certificate for itself, with a key pair consisting of a private key and a public key. The private key is kept secure by the certificate authority, while the public key is included in the certificate. This initial certificate is self-signed and acts as the starting point in the trust hierarchy. It's known as the root certificate authority, root CA. Using the root CA, the certificate authority can issue, sign, and manage certificates for various purposes, such as client or server authentication. Now, when an entity needs to trust this certificate authority, it starts by generating its own X509 certificate locally. It creates a corresponding public and private key pair and keeps the private key secure. Remember, whenever you create X509 certificate, a new key pair is generated. The public key is always included in the certificate, but the private key must remain private and secure. Next, the entity sends a certificate signing request CSR to the certificate authority. This request includes the certificate and the public key but not the private key. The certificate authority then uses its private key to sign the certificate and establishing a trust. Once signed, the certificate authority returns the signed certificate to the entity, which can then use it for secure communications and authentication. Now that we understand what an X500 certificate is and the role of a certificate authority, let's look at how the chain of trust works. Imagine we have the trusted certificate authority and its self-signed root CA. Client A generates an X509 certificate with its own public and private key pair. It sends a certificate signing request to the root certificate authority for signing. The root CA signs client A's certificate with its private key, and this certificate becomes an intermediate certificate. Now, client B generates its own X509 certificate with its key pair, and sends a certificate signing request to client A, not directly to the root certificate authority. Client A signs client B's certificate with its private key, and this certificate is known as an end-user certificate. This setup forms a chain of X509 certificates rooted in the root CA. So how does the chain of trust actually work? Let's break it down. Bob trusts the root certificate authority because he recognizes and trusts the organization behind it. Because client A holds an X509 certificate signed by the root certificate authority, Bob also trusts the client A. Furthermore, since client B has a certificate signed by client A, Bob trusts client B as well. And this illustrates the chain of trust for X509 certificates. If Bob trusts the root certificate authority, he trusts every certificate in the chain. Now, in the context of OAuth 2, Bob represents the authorization server, which needs to trust a specific root certificate authority and verify the client's X509 certificates to issue an OAuth 2 access token. Don't worry, we will explore this in detail shortly. Before we move on, let's touch on how X509 certificate verification works, because this is crucial for understanding how the authorization server checks certificates. The root certificate authority can verify client A's certificate using its public key, because the client A's certificate was signed by the root certificate authority's private key. Similarly, client A can verify client B's certificate using its public key, because client B's certificate was signed by client A's private key. So for the verification of an X509 certificate, the authorization server only needs to store the root CA in its trust store to verify incoming certificates. The client must send the entire certificate chain to the authorization server for successful verification. Now that we have covered these fundamentals, let's move on to see how this process works in detail. As always, we start with the OAuth 2 roles. The client sends a POST request to the token endpoint of the authorization server to obtain an OAuth 2 access token. The curl command for this process is similar to the one used in the standard client credentials flow, but without any secrets or authentication parameters included in the request body. The authorization server verifies the request, and if everything is valid, it returns an OAuth 2 access token to the client. But how does this process work without including the certificates in the POST request? This is where mutual TLS protocol comes into play, showcasing its strong security compared to other client authentication methods. The authentication doesn't occur within the request itself at the application layer, but instead at the TLS layer. If you are familiar with the OSI model, it includes 7 layers. In the host layers, we have the transport, session, presentation, and application layers. With MTLS, client authentication is completed before the communication reaches the application layer. It occurs as the session and application layers as part of the TLS layer. Here is the completed curl command that includes the certificates. These certificates are not part of the HTTP request body, but are used during the MTLS handshake to exchange certificates and drive keys. Once the handshake is completed and the client is authenticated, it can then execute the POST request to obtain an OAuth 2 access token. If everything checks out during the TLS handshake, the authorization server generates an OAuth 2 access token and returns it to the client at the application layer. I will not go into deep detail about MTLS here, but let's briefly review a sequence diagram to understand how the authentication process works. In MTLS, we have a client and a server. Both the client and server maintain a key store and a trust store. This is because in MTLS, both need to exchange and validate each other's X509 certificates. A key store holds the public and private keys of the certificate and includes the entire certificate chain if there is one. On the other hand, a trust store contains trusted root certificate authorities. These are used to validate the signatures of incoming certificates. The TLS protocol operates on top of a reliable transported protocol, like TCP. After that, we have the TLS layer, where MTLS takes place. And then on top, we have the application layer. The client initiates the process by sending a client hello message. This message includes information to secure and establish the connection. The server responds with a server hello, sending similar information and providing its certificate while requesting the client's certificate. The client validates the server's certificate using the root certificate authority in its trust store, which holds the public key. Then the client sends its own certificate back to the server. Next, the server validates the client's certificate using its trust store, which also includes the necessary root certificate authorities. If everything matches up, both the client and server calculate a symmetric key. This establishes an encrypted secure channel to exchange data at the application layer. So how does it fit into OAuth 2? In this context, the client is the OAuth 2 client, and the server is the OAuth 2 authorization server. By the time we reach the application layer, the client is already authenticated. It can now make a POST request, such as in client credentials flow, without providing any further client authentication in the request body. The authorization server validates the request, and if everything checks out, responds with an OAuth 2 access token. Now let's quickly recap the different client authentication methods we have covered in this chapter. First, client authentication using a client secret. This is the simplest and most standard method for confidential clients. It uses a static predefined client secret as an application password. While it's easy to implement, it's less secure because static secrets are vulnerable to compromise and don't have dynamic security features like expiration or rotation. Next, client authentication using a JWT bearer assertion. Here, the client authenticates itself by presenting a dynamically generated unsigned JWT token. The token can be issued locally or by an external identity provider. JWTs are more secure than static secrets because they expire and are signed with asymmetric signing, offering the highest protection against key compromise or replay attacks. Now, client authentication using a SAML bearer assertion. This method uses a signed SAML assertion for client authentication, issued either locally or by an external SAML identity provider. While it's secure and good fit for organizations with existing SAML infrastructure, it's less flexible and modern compared to JWT assertions. It's particularly ideal for legacy systems that rely on SAML. Finally, client authentication using an X509 certificate with MTLS. This method involves both the client and server authenticating each other using X509 certificates within the TLS layer. It ensures end-to-end security for the entire communication channel. While it's the most secure method, it's also the most complex to implement due to the certificate management requirements and reliance on a robust PKI. Let's now compare the different client authentication methods based on the most relevant key criteria. First, security level. Client secret has a low security level because static secrets are vulnerable to compromise. JWT bearer assertion and SAML bearer assertions provide medium security as they dynamically signed tokens or assertions. X509 certificates with MTLS offer very high security, ensuring both communication integrity and mutual authentication. Next, complexity of implementation. Client secret is the simplest to implement. JWT bearer assertions are moderately complex, requiring the ability to generate unsigned tokens. SAML bearer assertions are more complex, particularly for organizations without an existing SAML infrastructure. X509 certificates with MTLS are the most complex, requiring robust PKI and certificate management. This can be particularly challenging for systems using load balancers, as TLS termination often occurs here. You need to carefully evaluate your existing infrastructure to avoid introducing vulnerabilities or misconfigurations. Client capabilities needed. Client secret requires the ability to store static secrets securely. JWT bearer assertions require the capability to generate and sign JWTs. SAML bearer assertions require handling SAML assertions and integration with a SAML identity provider. X509 certificates with MTLS require managing certificates and PKI infrastructure, making it most demanding in terms of operational overhead. Risk of key compromise. The risk is high with client secret because static secrets are prone to exposure. JWT bearer and SAML bearer assertions mitigate this to a medium level by using short-lived signed credentials. X509 certificates with MTLS minimize the risk to low, as both parties authenticate each other and certificates are harder to compromise. Finally, mutual authentication. Client secret, JWT, and SAML bearer assertions don't provide mutual authentication. X509 certificates with MTLS are unique in providing mutual authentication, ensuring that both the client and the server verify each other's identity. There is no one-size-fits-all rule for selecting an authentication method, because the choice depends on the project's specific requirements and context. That's why we have the comparison table to guide the evaluation of these methods across multiple factors. However, here are some general guidelines to help you determine which authentication method might be suitable for different scenarios. Two key conditions must always be met when choosing any method. The client must be confidential, and the OAuth 2.0 authorization server must support the chosen client authentication method. Use client secret authentication if simplicity and quick implementation are priorities. When the security requirements are minimal. In cases where clients lack the capability to handle more complex authentication mechanisms. When time and budget constraints necessitate a simple solution. Use JWT bearer assertions if enhanced security is required. When the clients have the capability to generate and sign JWTs. If you need advanced token features like expiration and rotation for better security management, when there is a moderate amount of time and budget available to implement this method. Use SAML bearer assertions if enhanced security is required, when there is already an existing SAML infrastructure in place, if integration with SAML identity providers is necessary to align with organizational systems, when there is adequate time and budget available for implementing and maintaining this approach. Use X509 certificate with MTLS if maximum security is essential, as this approach ensures end-to-end communication security. When the organization can manage a robust public key infrastructure effectively, since MTLS relies on certificate-based management. If compliance requirements dictate strict security measures such as in regulated industries. When there is sufficient time, expertise, and budget available to implement and maintain this more complex solution. In conclusion, selecting the right client authentication method requires careful evaluation of your project's unique needs and constraints. By understanding the trade-offs and aligning them with your security, complexity, and budget requirements, you can make an informed decision to ensure secure and efficient authentication. In this chapter, we are going to explore advanced token security mechanisms. After successfully completing authentication and authorization, the client obtains an OAuth 2 access token from the authorization server. This token is used to send requests to the resource server. This process is common across all OAuth 2 flows. For example, in the authorization code flow, the client receives an access token from the authorization server, which it can use as proof to access resources on the resource server. Similarly, in the client credentials flow, the client receives an access token directly and can immediately use it to request resources from the resource server. But what happens if the access token is intercepted or ends up in the wrong hands? An attacker could then use the access token to impersonate the client and send requests to the resource server. The resource server would validate the token, confirm it's valid, and send back the requested resources, effectively enabling the attacker. This scenario is technically correct because the token is valid, but it is definitely not what we want. And this brings us to the critical question: how can we ensure that the access token is used only by the intended client? This is exactly where advanced access token security mechanisms come into play. In OAuth, there are two mechanisms that address this issue. X500 mutual TLS, MTLS, and demonstration of proof of position DPoP. Both mechanisms are part of the FAPI2 standards, which aim to enhance security and interoperability in high-risk environments such as financial services. We have already discussed X509 MTLS in previous lessons as a client authentication method. Now we will explore how it functions as an advanced token security mechanism. In simple terms, X509 MTLS ensures secure access token binding by leveraging the TLS layer. During the TLS handshake, the client presents its X509 certificate, and the access token is issued with a CNF confirmation claim that includes a hash of this certificate. This binding ensures that the token can only be used with the same certificate that was presented during the handshake. When the token is presented to the resource server, the server validates the certificate against the CNF claim to confirm that the token is being used by its rightful owner. In contrast, DPoP operates at the application layer. To start, the client generates a key pair, a private key and a public key. The access token includes a CNF claim containing the hash of the client's public key. For each API call, the client must provide a DPoP proof, a signed JWT generated using the private key, corresponding to the public key in the CNF claim. The resource server validates the DPoP proof and the CNF claim to ensure that the token is bound to the client and cannot be misused. This approach doesn't rely on the transport layer, but instead uses cryptographic proofs at the application layer. Now that we have introduced the two mechanisms, let's dive deeper into the X509 MTLS approach. Now that we have introduced these two mechanisms, let's dive deeper into the X509 MTLS approach. Before we begin with this flow, I want to highlight the importance of the earlier lessons on X509 MTLS in the chapter on the client authentication methods. If you haven't watched those lessons yet, make sure to review them first, as this lesson builds upon those foundational concepts. The first requirement for this mechanism is that the client authenticates itself using the X509 MTLS method. As always, we begin with the OAuth 2 rules for the client credentials flow: the OAuth 2 client, the authorization server, and the resource server. Each of these entities has its own key store and trust store. If you recall from the basics, a key store holds the public and private keys of the certificate and includes the entire certificate chain if applicable. Each server has its own key pair. A trust store, on the other hand, contains trusted root certificate authorities, which are used to validate the signatures of incoming certificates. The flow begins when the client wants to obtain an access token. To do this, the client authenticates itself using the X509 MTLS method, as discussed in the X509 MTLS lesson. This flow starts on the TLS layer, where the TLS protocol is performed. During the TLS handshake, the client and the authorization server exchange their certificates. At the conclusion of this handshake, the authorization server has confirmed that the client possesses the private key corresponding to the public key in its certificate, without ever exposing the private key. This is the strength of the X509 MTLS mechanism. Next, we move to the application layer, where the post request to obtain an access token is executed. If everything went smoothly at the TLS layer, the authorization server is now ready to generate an access token. Up to this point, everything aligns with what we have already covered in the X509 MTLS lesson as a client authentication method. The difference here is an extension of the flow, the feature of binding an access token to the client certificate. To achieve this, the authorization server calculates a thumbprint, a hash of the client certificate, and includes it in the access token within the CNF confirmation claim. Here's an example of a JWT access token with an additional CNF claim that contains the client's thumbprint. If we are not using a JWT access token, but instead an opaque token, this mechanism still works. In such cases, the CNF information is stored on the authorization server. Assuming we are using a JWT access token, the authorization server then returns the token, which now includes the CNF claim, to the client. Next, the client attempts to access resources on the resource server. To do this, it doesn't just present the access token, it also authenticates itself to the resource server using the X509 MTLS method, just as we have seen before. This involves performing the TLS handshake and exchanging certificates. At this stage, the resource server confirms that the client possesses the private key corresponding to the public key in its certificate, again without exposing the private key. Now we proceed to the application layer. The client sends a request to the resource server to obtain resources. As usual, the request includes the access token in the authorization header. But now it also includes the additional CNF claim. The resource server then validates the access token as usual. However, in this case, it also verifies the CNF claim within the token by calculating the thumbprint of the client certificate presented during the TLS hand check. It then compares this calculated thumbprint with the one included in the CNF claim of the access token. If these values match, it confirms that the token is bound to the client presenting the certificate. If they don't match, the token is rejected. This ensures that the token is bound to the client that possesses the corresponding private key. Note that if an opaque token is presented here, the CNF can still be verified by querying the authorization server which stores this information. The specific implementation details for this process depend on the OAuth 2 authorization server you are using. Now let's wrap up with the scenario where an attacker intercepts and steals the access token from the client. At this point, the access token is already bound to the client certificate through the CNF claim included in the token. The attacker, having intercepted the token along with the CNF claim, attempts to use it to access resources on the resource server. To do so, the attacker must authenticate using MTLS. The attacker has their own key store and trust store, but the key pair is certainly not the same as the client's key pair. The attacker sends a request to the resource server. Once again, the process begins at the TLS layer where the TLS protocol is performed. During the TLS hand check, the attacker masquerading as the client and the resource server exchange certificates. At the conclusion of this hand check, the resource server confirms that the presented certificate is valid and that the requester possesses the private key corresponding to the public key in the certificate without exposing the private key itself. However, if the certificate authority that issued the attacker's certificate is not trusted by the resource server, the request will be immediately rejected as unauthorized. Now, let's assume the attacker's certificate is from a trusted certificate authority and passes the TLS layer validation. The resource server then proceeds to validate the access token and verify the CNF claim. This is where the issue arises for the attacker. The CNF claim in the token doesn't match the attacker's certificate because it's bound to the client certificate. This mismatch results in the resource server rejecting the request as unauthorized, effectively preventing the attacker from using the stolen token. Now, let's explore how DBOB binds the access token at the application layer without relying on certificates. As always, we start with the OAuth 2 roles in the client credentials flow. The OAuth 2 client, the authorization server, and the resource server. The client initiates the flow by generating a key pair, a public key and a private key. Using this key pair, the client then generates a DBOB proof. A DBOB proof is a JWT, so it contains three components: a header, a payload, and a signature. The header includes three parameters. Type. This specifies the type of the token, which in this case is DBOB, indicating that it is a DBOB JWT. Algorithm. This indicates the algorithm used to sign the token. Ensure that this algorithm is supported by the authorization server for DBOB tokens. JWK. This contains the public key associated with the private key used to sign the token. The header is generally static and only changes if you use a new key pair or a different signing algorithm. The payload is dynamic and it changes with each request. It includes the following parameters: JTI, JWT, ID, a unique identifier for the DBOB proof, ensuring that each proof is distinct. HTM, HTTP method, the HTTP method of the request, such as a post, which is used in this case. HTU, HTTP URI, the URI of the target endpoint for the request, such as the authorization server's token endpoint in this flow. IET issued at a timestamp indicating when the DBOB proof was created. This ensures that the proof is valid only for a specific time window. Finally, the client signs the header and payload using the private key from the key pair. This signature ensures the integrity of the DBOB proof. The signed JWT is then base 64 encoded, resulting in the DBOB proof, which the client can now use in the subsequent flow. The client sends a POST request to the token endpoint, including the DBOB proof in the request header, to obtain an OAuth 2 access token. Here's how the curl command looks. The POST request is sent to the authorization server, targeting the token endpoint. In the request header, we include content type is set to URL encoded from data, DBOB containing the base 64 encoded DBOB proof JWT. In the request body, we include the typical parameters for the client credentials flow. Grant type set to client credentials, the client ID and the client secret, optionally the requested scopes. This mechanism can also work with the authorization code flow for both public and confidential clients. If the client is public, it doesn't need to include the client secret for authentication. The authorization server first validates the client credentials and then verifies the DBOB proof. It checks the claims in the payload, ensuring the request context, for example HTU and HTM, align with the current request. It also verifies the proof's signature by extracting the public key from the DBOB JWT and using it to verify the signature. This ensures that the client holds the corresponding private key without exposing it. If everything checks out, the authorization server generates an OAuth 2 access token. It calculates a thumbprint, a hash of the public key from the DBOB proof, and includes it in the CNF confirmation claim of the access token. If the access token is not a JWT but an opaque token, the CNF information is stored on the authorization server. Assuming we are using a JWT access token, the server returns the token now containing the CNF claim to the client. Now the client needs to make a new request to the resource server. For this, it generates a fresh DBOB proof. As mentioned earlier, a new DBOB proof must be created for each request. The header of the DBOB proof remains unchanged, but the payload reflects the new request context. The HTTP method as a GET, the URL of the resource server's protected endpoint, and the new issued at time. Additionally, the payload includes the ATH claim, which binds the DBOB proof to the OAuth 2 access token. The ATH is the hash of the access token and ensures the DBOB proof is uniquely tied to this specific token. This prevents token substitution attacks and cross-token misuse. The client then sends a GET request to the resource server, targeting the protected endpoint. In the request header, it includes the OAuth 2 access token, prefixed with DBOB, and the new DBOB proof JWT. At this stage, the resource server validates both the access token and the DBOB proof. It verifies the CNF claim in the access token. To do this, it calculates the hash of the public key provided in the DBOB proof and compares it to the CNF in the token. If they match, the token is confirmed to be bound to the client making the request. If not, the request is rejected. Next, the server verifies the ATH claim in the DBOB proof. It calculates a hash of the presented access token and compares it to the ATH value in the proof. This ensures the DBOB proof is specifically bound to the access token being used. If the value don't match, the request is rejected. If all validations are successful, the resource server grants access and returns the requested resources to the client. By requiring a unique DBOB proof for each request, reply attacks are prevented. Binding the token to the client via CNF claim prevents token swapping, while binding the DBOB proof to the access token via the ATH claim protects against proof misuse. This comprehensive binding mechanism ensures robust security throughout the flow.